has a name, Google.
Why does that, you know?
The point is that the environment in the blood vessel is different from the environment outside of the blood vessel. So outside, we have some things that we don't have inside. And one of those things I'm going to draw here. I'm drawing it here, and it has a name. It's called collagen. So I'll write that down here. It's called collagen. You don't have to worry too much about what it is. Collagen is kind of a structural protein that your body uses to give structure to things. And so the important thing is you have collagen down here, and you don't have it here. You don't have it here. You don't have it here. And it turns out that collagen chemically interacts with the platelets. And maybe we'll draw a little spark there to show that they're chemically interacting. It chemically interacts with them and causes them to stick together and form this plug that we're talking about. So we can call this, by the way, a platelet plug, because it's plugging the hole. And by the way, just to be clear, you also have collagen up here and over here. So it's basically everywhere outside the blood vessels. Now, it turns out that this is only step one of the clotting mechanism of your body. So up here, we'll put number one, platelet plug. And there's actually two steps, because the platelet plug itself is not quite as strong as we would like it to be. So there's a second step, which makes this plug stronger. And that second step involves something called fibrin. So we'll write that here, fibrin. And fibrin is not a little mini cell like platelets are, or a fragment of a cell like platelets are. Fibrin is just a protein. And what fibrin is going to do is it's going to come here and it's going to try to strengthen this plug by forming this mesh of protein that's going to hold all these platelets together and form a very tight object. Now, these fibrin strands, that's what each of these little squiggles is, it's a fibrin strand. These fibrin strands are made up of little fibrin subunits, which I'll draw here. And it turns out that these subunits naturally like to come and stick together. And I guess the technical word for this is they polymerize, they form a polymer. Basically, they just stick together, and lots of them will stick together in a line to give you this fibrin strand we see here. And where does this fibrin come from? Does it come from down here? No, it actually also circulates in the blood. So let's draw some little fibrin molecules up here. So they're circulating in the blood. Is this right? Well, this actually can't be exactly right, because I just told you that these fibrin molecules naturally stick together. And so if we had these fibrin molecules circulating in the blood like this, what would happen? Well, they would actually stick together in the blood, and they would form these long strands in the blood that we didn't want, because we only want the strands here at the platelet plug. So let me remove those strands. So it turns out that we don't have fibrin circulating in the blood. What we have is something slightly different. We have fibrinogen. Fibrinogen. And so I'll draw a fibrinogen down
So we
here.
have kind of a little cap.
Of course, keep in mind, these are all my little cartoons, and probably it doesn't look like this. So these guys we said were fibrin. But now this molecule is a fibrinogen. And you'll notice it's the same as a fibrin, except it has an added little piece to it. And that little piece, as you can tell, is going to keep it from sticking to itself. These fibrinogen are not going to be able to stick together the way that these fibrin are. So what do we need to do then? Well, of course, we need to turn this fibrinogen into fibrin. So where are we going to do that? Only at the site where we want fibrin strands to gather. So only here where we have that damage. And so again, we face the same question that we faced with the platelets, which was how do the platelets know to aggregate here? Well, likewise, we want to know how do the fibrinogen know to turn into fibrin here so that they can then stick together and form the strands? And the answer basically is luckily the same. So we have some chemicals down here. Now we're not talking about collagen anymore, we're talking about something else. And if you really want to know what it is, I'll write it here. It's not really the name that's important, it's the principle here. The principle is you have these little proteins down here called tissue factor. And they're normally not in the blood. They're only down here outside of
tissue
the
factor,
endothelial.
and then goes along with 7.
Cells
TF7
lining the blood vessel. And so these little proteins, tissue factors, are going to be right here in this little wound and around the wound, and they're going to cause these fibrinogen to become little fibrin protein molecules, and then those fibrin will be able to stick together, and they also stick to the platelets, by the way. I hope that's clear about that, and form the mesh that we see there. Now, if we want to get really fancy, we can ask, how does tissue factor turn fibrinogen into fibrin? And you can ask, is tissue factor kind of like a little knife? Is it, by knife I really mean enzyme, is it a little knife or enzyme that causes this piece to break off of the fibrin so that we're left with just fibrin? And actually, unfortunately, the story is much more complicated than that. And there's actually a good reason for it. Because let me propose to you a situation. Let's say you have to turn 1,000,000 fibrinogen into fibrin. Because each of these fibrinogen is a very small protein, so we need about 1,000,000 of them to make up this polymer. And let's say that you are tissue factor. So if you are tissue factor and you want to turn 1,000,000 fibrinogen into fibrin, is the best way to do it for you to actually sit down and chop off this piece off of all these fibrinogen one by one? That would take you a long time. Is that better, or is it better for you as tissue factor to call up 5 friends and have each of those friends call up 5 friends and have each of those friends call up 5 friends and keep doing that until you have a huge number of people that are ready to help you, and now get all of those people to help you convert fibrinogen to fibrin? So obviously that latter scenario is a more efficient mechanism. And so that's what your body does, and that's what tissue factor does. So tissue factor, and by the way, I know this is getting convoluted, but try to stick with me. Tissue factor is going to turn another protein that we haven't talked about into its active form. And then that other active form of that protein that we haven't talked about is going to activate another protein that we haven't talked about into its active form. And then that one is going to do the same, and then that one is going to do the same. And so basically every time you introduce a new protein in there, you're ramping up the total number of activated proteins of that type. And so finally, by the time you get to the one that's going to break the fibrinogen apart and create fibrin, and by the way, I'll draw him, and he has a special name called thrombin. Again, I don't think thrombin is necessarily a word you need to know, but just in case. So by the time you get to thrombin, you have a lot more activated thrombin than you had tissue factor in the beginning. But the tissue factor here is the spark, and that's the guy that really got us going. So that's basically it. This is how your body plugs holes in blood vessels and keeps you from losing too much blood. And if you want to know more about that kind of complicated stuff I said at the end, about all these different levels of activated proteins, you can look it up. It's called the coagulation cascade. It's called a cascade because you're cascading through all these different levels of proteins. Let's say this is a blood vessel, and it's made up of these endothelials.
15, 10.
Cells, the same way that all blood vessels are. And let's say that this blood vessel gets into a fight, and it gets a little bit hurt. So the walls break open, and the cells now no longer seal the vessel from what's around it. When this happens, we wouldn't want all the blood in this vessel to come pouring out of the vessel, because we'd lose way too much blood. And so the body has a method of containing the blood. The first thing that's going to happen is that little platelets, which are circulating in the body, are going to come and deposit there and form an initial plug. So these little things are platelets. But it turns out that this plug is not quite solid enough, and so the body needs a second mechanism to solidify the plug. And that mechanism is what we're going to talk about most of this video. And I'm drawing that mechanism here. What I'm drawing is little fibrin strands, which will come and act as a kind of mesh to hold the platelet plug together solidly. So what do these fibrin strands look like? Well, they're made up of little fibrin subunits. And these are actually what we refer to as the fibrin molecules or proteins. And these, it turns out, have a natural affinity for each other, so that when you bring them together, they form a polymer. They join end to end, and they create a fibrin strand. So the question then becomes, how do you make sure that these fibrin units only join together and make a strand at the site of injury? So for example, if you had a bunch of little fibrin molecules over here, how would you keep them from joining together? And the answer is that you can't, which is why you don't have fibrin circulating in your blood. You actually have something else, which I'm going to draw here. And that something else is fibrin, but plus an extra piece. And that extra piece, as you can see, covers one of the active sites of fibrin and therefore prevents it from joining to itself. So the name of this thing is fibrinogen, probably because it will form fibrin, hence the fibrinogen. And it's only when you convert fibrinogen to actual fibrin that the units can join together and form a strand. And so again, to repeat, you don't have fibrin circulating in your blood. You actually have fibrinogen. So the question then becomes, how does your body know to convert fibrinogen into fibrin at the site of injury? And the answer is that when you injure your endothelium here, you're going to expose your blood to new proteins. And maybe your actual endothelial cells will release some proteins because they're damaged. So basically, you have new proteins that weren't seen before and that are seen now. and those proteins will eventually cause fibrinogen to turn into fibrin. So while evolution was designing us, it could have said, let's use these little yellow guys to convert fibrinogen to fibrin. And that might have worked, but it's actually not the most efficient way to do things. And the reason is, imagine if you and a couple of friends have a huge amount of work to do. Let's say you need to convert 1 million fibrinogen to fibrin. Is the best way to do it to actually sit down and crank it out? Or would it be more efficient to have each of you call 5 friends, invite those friends to come work, and ask those friends each to call 5 friends, and ask those friends to each call 5 friends? Well, obviously that would get the job done much faster, assuming you had those friends. And that's also what your body does. So actually, it doesn't use these yellow guys to convert fibrinogen to fibrin. There's another player which does that, and it's an important one, so we'll give it a little drawing like that. And it is called thrombin. And thrombin, just like fibrinogen, is activated from an inactive form, which we call prothrombin. And the prothrombin has a little piece on the end that prevent that would get the job done much faster, assuming you had those friends. We'll give it a little drawing like that, and it is called thrombin. And thrombin, just like fibrinogen, is activated from an inactive form, which we call prothrombin. And the prothrombin has a little piece on the end that prevents it from working. So this is prothrombin, and that piece is removed when you want to get to work. So is prothrombin activated by the little yellow guys? Well, actually, he's not either, because the chain of amplification is much longer than that. To draw the actual amplification cascade, you just need to see it and practice. But there is an easier way to draw it than it usually is drawn, so we'll do that now. So let's say you were counting down from 12. Normally you would start 12, you go to 11, you go to 10, and then you go to 9. But let's say that you weren't very good at counting. You would start with 12, you go to 11, and you make a little mistake, you go to 9, then you realize you forgot 10, and so you go to 10. Now it's good that you remember 10 because 10 is a big deal, and he's going to help bring us thrombin. Turns out that thrombin is also known as 2. And we know very well that thrombin helps give us fibrin, which is known as 1. And that's no surprise because fibrin is the most important guy, he's the ultimate goal, and thrombin is the guy that helps us get the ultimate goal, so he should be number 2. Now unfortunately it's not quite that easy. 10 likes 5 because they're both multiples of 5, so they work together, and 9 likes 8 because they're right next to each other, and so they work together. So this is the first part of our clotting cascade, and it turns out that we call this part here the intrinsic pathway. And we can talk about what that means later, but for now let's just give it its name. But what's perhaps more important to be clear about is that in this drawing, 12 is not actually becoming 11, and 11 is not actually becoming 9. What's happening is that 12, when it's activated, is a catalyst to convert 11 from its inactive form into its activated form, which we'll draw 11a. And then once 11 is activated, it serves as a catalyst to convert 9 from its inactivated form into its activated form. And so you see that these arrows are actually more about catalyzing. Now I said that this was an amplification sequence, and so I just wanted to share a little data to show that that's true. So it turns out that this guy, factor 1, or fibrin, in its inactivated form, which is fibrinogen, has about 3,000 micrograms per milliliter in blood, while this guy has about 100 micrograms per milliliter in blood. Meanwhile, 10 has about 10 micrograms per milliliter in blood, and factor 9 has about 5 micrograms per milliliter in blood. And so you can really see that as you go down this thing, you're increasing your amounts in your blood, which reflects the fact that you're also going to increase the number of active forms of these when you have a clot. But anyway, I said that this was the intrinsic pathway because there is another pathway, which also leads to an activated 10. But in this other pathway, what activates the 10 is an activated 7, which is activated by 3, also known as tissue factor. I'll just write TF for tissue factor. And this pathway, which I'll circle here, and I apologize for the poor organization.
7.
This one is known as the extrinsic pathway.
Yeah. Okay.
Extrinsic. So what's the difference between these two pathways? Well, it turns out that the extrinsic pathway is the spark. It's the one that gets activated by the original insult over here, whereas the intrinsic pathway is kind of like the workhorse. It really gets most of the coagulation done. So how does that work? Well, you first get this tissue factor, which is actually one of these little yellow guys. And that tissue factor activates 7, which activates a little 10, so you get a shot, a spark that shoots down this way. and activates a little bit of 10, and then 10 will activate a little bit of thrombin, and then thrombin will get the intrinsic workhorse going. And how will thrombin do that? Well, thrombin actually activates a whole bunch of these guys. And to remember the ones that it activates, you just need to take the 5 odd numbers starting at 5. So what is that? That's 5, 7, 9, 11, and 13. Actually, this is just almost right, but it actually turns out that it's not 9, it's 8. Because it couldn't be quite that easy. So those are the 5 that it activates. And so let's draw that in here in our drawing. So let's draw that in the form of blue arrows. Blue. You said it's going to activate 5. You said it's going to activate 7. You said it's going to activate not 9, but 8. So this will be an awkward arrow to draw. We said it's going to activate 11, and we said it's going to activate 13. Where's our 13? Well, we haven't actually drawn it in yet. So let's quickly chat about that. The end goal of this whole cascade is to get these fibrin molecules. And these fibrin molecules together will form some strands. But it actually turns out that there's one more step, which is to connect these strands together. And so we're going to want to connect these strands together with some crosslinks. These crosslinks will just hold them together so that they actually form a tight mesh. And it turns out that it's this step right here, which is enabled by factor 13. And so let's draw the final thrombin activity, which is to activate 13. So you can see that once you activate a little thrombin, it's going to activate all the necessary things in this intrinsic pathway to get it going. And you might actually be wondering about 12 up there, because thrombin is not hitting him. And actually, it turns out that if you remove a person's factor 12, they can still clot pretty well. And so it's clear that 12 is not a totally necessary part of this intrinsic pathway. And to be clear again with our use of arrows, this green arrow here is different from these white arrows in the sense that here we are saying that fibrin is going to become fibrin strands, which is going to become interlaced fibrin strands. So if this was all there was to the story, then every time you had a little bit of damage to your endothelium, you would cause the extrinsic pathway to fire. And so you would create a little activate 7, you would activate some 10, which would activate some 2, which is thrombin, which would start to create fibrin from fibrinogen. And moreover, the thrombin would have this positive feedback, which would cause more and more thrombin to be produced, which would cause more and more fibrin to be produced. And basically, this system would just spiral out of control and you would become one large walking clot. So to keep that from happening, there are some negative feedback loops. And like much of the other steps in this picture, they're governed by thrombin. So one thing that happens is that thrombin helps create plasmin from plasminogen, much the way it helps create fibrin from fibrinogen. And this plasmin acts directly on these mesh networks of fibrin and breaks them apart. So that's one helpful factor, but that's not really an example of negative feedback because it won't prevent the continued production of all this. And so another example is that thrombin actually stimulates the production of antithrombin, which is kind of counterintuitive, but that's sort of classic negative feedback. And what antithrombin is going to do, as you could guess, is it's going to decrease the amount of thrombin that's being produced from prothrombin, and it's also going to impede the production of activated 10 from 10. So what if this whole system didn't work? I don't mean the negative feedback, but I mean the whole clotting system. Well, if it didn't work, then you wouldn't form a stable plug here, and you would get lots of blood pouring out of your damaged endothelium. And so what we call that is hemophilia. Hemo refers to blood, and philia means love. So people who have hemophilia love to bleed. And there are 3 different kinds of hemophilia. There is A, there's B, and there's C. And it's easy to remember the causes of these because A is associated with 8. B is associated with what comes after 8, 9. And C is associated with what comes after 9, not 10 actually, but 11. And so we can draw those into our clotting cascade over here to see that a factor 8 deficiency will give you hemophilia A, a factor 9 deficiency will give you hemophilia B, whereas a factor 11 deficiency will give you hemophilia C. And so we see that these guys target the intrinsic pathway. So here's a guy, and like any guy, if we look at a little bit of his blood, let's say we look at 1 microliter of his blood, 1 microliter, and there are, of course, 1 million microliters in 1 liter. If we look at just 1 microliter, what will we find? We'll find about 5 million red blood cells, 5 million for every microliter. And actually, by percent of volume, the blood cells make up about, maybe 40% of the blood. There's a lot of them. There's 5 million in 1 microliter red blood cells, just write RBCs. And in that same microliter of blood, there will also be platelets. Now, do you think there will be more or less platelets than red blood cells? So platelets are a lot smaller, so you might think that there could be more, but actually there is less. Usually it can range quite a bit, but a number you might see is 200,000 platelets in 1 microliter, and that's platelets. Those are the little guys that help make clots when you have problems with your blood vessels.
Mm.
So let's say this guy is 20 years old. Do you think that his red blood cells and his platelets are the same ones that he had 5 years ago? Actually, they're not, because both of these things get kind of destroyed. They break down at a certain rate. And so this guy needs to be constantly making new red blood cells and platelets. And actually, it turns out that red blood cells last about 120 days on average. It's about 4 months. And platelets, meanwhile, only last a couple of days. So, a lot less than red blood cells. So you need to be constantly making more of these things. And do you know where you do that? It turns out you do it in your bone marrow. So here I'm drawing a bone. And in the marrow inside that bone, that's where you produce these red blood cells and these platelets. Now, the way that red blood cells are made in the bone marrow is that they start from some precursor cell. So there's some kind of cell that's not a red blood cell. And one way it's different is that it has a nucleus. So in case you didn't know, red blood cells actually don't have nuclei when they're in circulation. So some precursor cell that has a nucleus. And I'm going to kind of simplify this a little bit, but basically, this precursor with a nucleus can divide. So it undergoes the usual process of mitosis to divide. And so now we have two. And actually, you'll do that many, 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 many times. So you'll have a lot of them. But then some of them can actually become what we know as red blood cells. And part of that process involves, as I said, losing the nucleus. So this whole process happens in here. So I'll draw some red dots to simplify that, to symbolize that rather. And then these blood cells will go into blood vessels. And we'll just draw some blood vessels here in this bone. Bones do have blood vessels in them. So they'll go into those blood vessels and go back out to circulation and eventually up into the heart, from where they'll get pumped out to the body. So this is red blood cells. And actually, there's a fancy name for red blood cells, which is erythrocyte. So let me write that here. Erythrocyte. Might be worth knowing, might not be worth knowing. But anyway, that's another name for red blood cell. And actually, this whole process of creating red blood cells can be called erythropoiesis. Erythropoiesis. And that just means creation of red blood cells. Now, platelets are made differently. Platelets are actually fragments of cells, and they come from a big cell called a again, more long words, megakaryocyte. The important thing about a megakaryocyte is that it's a big cell. It has lots of cytoplasm, that's the stuff that's not the nucleus. And the way the platelets are made is that they actually just
mega. Okay.
kind of bud off of the megakaryocyte. So they're bits of cytoplasm that bud off, and so they're obviously surrounded by membrane. And every megakaryocyte can do this many, 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 many times. And so they will release many little platelets in this manner. And then just like the red blood cells, these platelet cytoplasms can be called erythropoiesis. Erythropoiesis. And that just means creation of red blood cells. Now, platelets are made differently. Platelets are actually fragments of cells, and they come from a big cell called a again, more long words, megakaryocyte. The important thing about a megakaryocyte is that it's a big cell. It has lots of cytoplasm. Is that it's a big cell. Again, more. So they come from a big. Platelets are actually fragments of cells, and they come from a big cell called a again, more long words, megakaryocyte. The important thing about a megakaryocyte is that it's a big cell. It has lots of kind of bud off of the megakaryocyte. So they're bits of cytoplasm that bud off, and so they're obviously surrounded by membrane. And every megakaryocyte can do this many, 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 many times. And so they will release many little platelets in this manner. And then just like the red blood cells, these platelets are going to go into circulation and make their way throughout the body. So we said that red blood cells only last 120 days, and platelets only last a couple of days. So a question you might have is, what happens to them after that? Do they just disappear? Of course, they don't just disappear. They're in your bloodstream, and your body has to take them out. And so the organ that's most responsible for doing this is the spleen. drawing it here. As you can tell, it's on the left side of this guy's body, and it's sort of the upper part of his abdomen. And the spleen is just one of the places that blood goes from the heart. So the heart pumps and it sends blood to the arms, to your muscles, to your brain, to your legs, and it also sends some to the spleen. And when some of that blood passes through the spleen, and we'll draw a cartoon of that here, when it passes through the spleen is going to recognize the old red blood cells, the ones that are damaged and that are worn out, and it's going to take those out of circulation and basically chew them up and break them down and get rid of them. And the cells that do this are called monocytes. So let's just draw a quick cartoon of that. So here we have a red blood cell, which is old. So I'm going to draw it a little bit deformed. It's a little bit old and decrepit. And it's lived a good, long, happy life, and it's time for it to go. So in the spleen, it's going to get engulfed by a cell called the monocyte. I'll write that name here, a monocyte. I'm putting a lot of names out here. A monocyte is basically like a macrophage, if you've heard of that. It's quite similar. This monocyte in the spleen is going to phagocytose, or basically chew up this old red blood cell and break it down into its parts so that they can be reused. And I will mention that one of the things that needs to be reused, and I'll actually draw it here because I think this is important, is iron. So red blood cells have iron in them because that's part of hemoglobin. And your body doesn't want to lose that iron. So the monocyte is going to recycle that iron for further use, along with many of the amino acids that make up the proteins in the red blood cell. So let me just write recycle, because it's important to recycle and not to waste. Now I will mention that most of this happens in the spleen. Most of these red blood cells and platelets get broken down in the spleen, but it also happens a little bit in the liver, which is going next to the spleen here, and the process is quite similar. So this is how you get rid of old red blood cells and platelets. Now, how does your body know how many new red blood cells to make? Well, to answer that question, let's go back to what is the primary purpose of red blood cells. Their primary purpose is to bring oxygen out to the different parts of the body. So if you don't have enough oxygen, so say low O2, if you don't have enough oxygen, that means that you probably don't have enough red blood cells. And it could also mean that your lungs aren't working or something like that. But your body most of the time will interpret it to say, okay, we don't have enough oxygen, that means we need more red blood cells. So when there's low oxygen, your body's going to produce something that's going to tell the waste. Now I will mention that most of this happens in the spleen. Most of these red blood cells next to the spleen here, cells and platelets. Now, how does your body know how many new red blood cells to make? Well, to answer that question, let's go back to what is the primary purpose of red blood cells. Their primary purpose is to bring oxygen out to the different parts of the body. So if you don't have enough oxygen, so say low O2, if you don't have enough oxygen, that means that you probably don't have enough red blood cells. I mean, it could also mean that
How do you make that? What's the connection?
that your lungs aren't working or something like that. But your body most of the time will interpret it to say, okay, we don't have enough oxygen, that means we need more red blood cells. So when there's low oxygen, your body's going to produce something that's going to tell your bone marrow to produce more red blood cells. And that's something I'm going to write here. And it has a similar name to these other words up here. It's called erythropoietin. It's not erythropoiesis, it's erythropoietin, which stimulates this whole process and causes you to make a lot more erythrocytes, or red blood cells. And like I said, what causes the release of erythropoietin is low oxygen. And I should mention that that happens in the kidney. So let me just write kidney here. So the kidney is going to release erythropoietin. And you might have heard of erythropoietin. It has another name, which is EPO. That's a abbreviated name. And you might have heard of it because some athletes who feel that they need more red blood cells in order to get more oxygen to their muscles and perform better, some of those athletes will actually take EPO. They'll take EPO so that their bone marrow makes more red blood cells. And do you know what EPO might be called? Do you know what kind of substance it might be in our vocabulary of biology? Well, EPO is a hormone because it's a substance that communicates between, I guess, the kidney, basically really the whole body, and the bone marrow. And likewise, the platelet production system also has a hormone that controls it. And that hormone is called something else. It's called thrombopoietin. And that's a much less important name than erythropoietin. You're much less likely to ever hear thrombopoietin. But all I want to do is make it clear that production of platelets also is controlled by a hormone, just like production of red blood cells.
That's what the racer, the cyclist racer. Was it Neil Armstrong? Not Neil Armstrong. Lance Armstrong. Lance Armstrong. I think that's what he took, right? Back in the day. Lance Armstrong. To win the races and everything.
So let's draw a blood vessel. Here is a blood vessel. And in any human, you or me, there's lots of different blood cells traveling around in all the blood vessels of the body. So you've got your red blood cells that I'm drawing here. But you've also got your T cells, which are immune cells. You've also got B cells. You've also got something called a macrophage. You've got neutrophils. You've got little platelets, which are actually fragments of cells. They don't have their own nuclei. And all in all, you actually have about 10 different kinds of blood cells. And a question you can ask, which is what we're going to address in this video, is where do all these blood cells come from? Do you know? I'm going to draw the answer right now and see if you can figure out what exactly I'm drawing.
Bone.
So this is a bone, because all these blood cells in the body come from the bone marrow. And here's the bone marrow that I'm drawing here. Now, actually, it turns out that they don't come from all the bone marrow of the body. They come from certain places. Some of those places are the head of, for example, the femur, which is the long bone in your thigh, the head of the humerus, which is the long bone in your arm. Those are all long bones. And they also come from something called flat bones. These are very simple names, which I think is always good for us when we're learning a field. Flat bones, such as the one I'm drawing here, which is the sternum. The sternum is the flat bone in your body that connects to all of the ribs. Here are some ribs. Of course, it has ribs on both sides. So the blood cells come from these parts of the long bones and the flat bones of the body. And it turns out, which is interesting and which was not always known, it turns out that all these blood cells in your body have one common precursor, one grandfather, if you will. So there's one grandfather cell that gives rise to all of these guys. And I'll draw him here. So here he is, he's purple. And his name is complicated. He's called a pluripotent. Pluripotent. If you ever took a Latin, you might know that that means sort of able to do anything. Pluripotent, hematopoietic stem cell. And the reason that he's called pluripotent is that he's able to give rise to any of the 10 red or any of the 10 blood cells. So hematopoietic stem cell. You might recall that stem cells are sort of undifferentiated cells that can give rise to many different kinds of cells. So this grandfather cell gives rise to two different lineages. And those two lineages are the myeloid lineage and the lymphoid lineage. And each of these lineages gives rise to many different cells. So the myeloid lineage gives rise to red blood cells, which are biconcave in shape. They are the most common of all blood cells. Now, the myeloid lineage also gives rise to a big cell called a megakaryocyte. Now, you might never have heard of this before, but the megakaryocytes themselves produce platelets, which I think that you probably have heard of. So here are platelets. They're little fragments of cells which actually bud off of the megakaryocytes like this. They kind of squeeze out little pieces of cytoplasm that become platelets. And now I have a challenge for you. Do you think that a macrophage, which is an immune cell that likes to eat up invaders like bacteria, do you think that macrophages come from the myeloid lineage or the lymphoid lineage? So I was surprised to find out that they actually come from the myeloid lineage.
Okay.
I was surprised because macrophages are immune cells, but they actually come from the same lineage as red blood cells and platelets. So here is this is actually not yet a macrophage, this is a monocyte. A lot of crazy words here, but this is a monocyte. Monocytes actually become macrophages once they settle down in the tissues. But before that, while they're still circulating, they are monocytes. And in addition to the monocyte, the myeloid lineage gives rise to three guys, one of whom you have heard of probably, two of whom you may not have heard of. I'll just draw them here. So the one you might have heard of is I'm running out of space here, but it's the neutrophil. The neutrophils are the most common immune cell in the blood. The other two are called eosinophils, which are significantly more rare than neutrophils, and even more rare than eosinophils are something called basophils. So it's the three phils. So now let's go over to the lymphoid lineage. There's three important cells that come from this one. Two of them you've probably heard of. I'll draw them first. They're both lymphocytes, so it makes sense that they come from the lymphoid lineage, and those are B cells and T cells. If you recall, B cells are the guys that are going to put out this molecule. Do you know what that is? That's an antibody. B cells make antibodies. And T cells have their own functions that you can learn about in the immune system videos. Now, the lymphoid lineage also gives rise to something called, it actually has a very sort of dire, morbid name. It's called a natural killer cell. Sometimes we say NK, natural killer. So this is pretty much it. Here we've got our grandfather cell, who gives rise to two lines. We could call these maybe the father cells if you want. And these give rise to our whole array of blood cells. Some of them you've heard of, some of them you haven't. You'll hear more about the ones you haven't heard of in the future. There's one or two more I want to mention now that are maybe a little more complicated. We have something called a dendritic cell. And the reason I didn't mention it before is because the dendritic cells actually come from both sides, both lineages, which is confusing. They can come from the lymphoid, and they can come from the myeloid by way of monocytes. So monocytes can become dendritic cells. And then we also have another one coming from the myeloid lineage, which is actually fairly important. I could have mentioned it earlier. It's called a mast cell. And mast cells are most notable for causing allergic reactions. They release histamine. And you know, when you have an allergic reaction, you might take an antihistamine, and we do that so these mast cells can't make you feel crummy.
Let's go over to 114. $114 and $199. Is that right? What's your phone to do? What if I do 199 first? Since I went over a little bit ago. So we'll start here when I come back. And oh, good luck, Nadine. Good luck. Yeah, you got it. Good luck. I mean, it sounds like you were studying it really well, you know? Jack Weston and the cars and all the stuff you're telling me. I think you're going to do fine. Hopefully you get the score you want. Good luck. Yeah. That's pretty cool. Really cool, actually. Yeah, good luck. All right, anyways, we'll read this when I come back. I'm going to go get some food. 189, 114. We'll answer the questions, and we'll move on. And we'll just have to do these today. That's the goal. Yeah, so let's see. I think we can do it. All right, I'll be back. Just leave it here. I might zoom in on it actually. Just get up and down. I don't know how you want to. Spend that much time right now. Rex hasn't played. Just focus on this. Thanks. Also, thanks for those streams. I'm gonna stay on track. Yeah. Okay. Cool. I'm glad I helped you out, Nadine. Yeah. Good luck on the test. Awesome. Yeah. If I can help other people, great. Great. Fantastical. Fantastical. Okay, yeah, 199. Let's go. Getting kind of tough. Watching something. Actually, yeah, no, we should read it. Let's just read it, I guess. Ah, ah, oh! I bit my cheek. Oh man. I don't taste any blood, so I think we're okay. 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 Hold on, guys. Got pimped up. Okay. Excuse me. My back. Okay. The adhesion of the liquid tube. The adhesion of the liquid to the tube is greater. Hold on, guys.
You want some eggs?
Huh?
You want some eggs?
Eggs?
I should make them right now. Okay, enjoy.
Oh, we got a lot of food. All right. Okay, hold on, guys. I need to clean up. Okay, wait. Walk sign is on. Wait. Walk sign is on. Okay. Let's see if this is on. Look at that. Okay, where were we? This is a 199. Yeah. 203. And let's read 114. Sorry, 113? 14. This one. 114 to 120. Yeah. Okay, hold on, guys. Let's okay, hold on. Where's my spray bottle? I don't know why it is I keep losing stuff. It's not cool. Oh, sure. I think I'm just blind. I mean, that's true, though. I am blind. I am very, very blind. Um, okay. Particularly that at the primary protein structure level. Yes, sir. What the heck? Mm-hmm. Okay. Yeah. Bad guys. Can't see. You guys weren't able to read it. Anyways, we just. Oops, sorry about that. We just finished reading 199. We just finished reading 199 through 203. And then we also just read 114. We also just read 114. Down through 120. So we're done. Now let's go ahead and just do these questions. check this distance. Which is I think it's so the top ones are less dense, which means that we either need to have a we're gonna have low mass. We also have to have, I guess, greater volume. So it's not greater density. This maybe. Greater mass. Greater mass. But what's its volume? We don't really know. And then didn't what was the volume? I think it was a little bit more plasma, right? I don't think so. Oh wait. Yeah. Actually, yeah, D is fine. Greater mass? Not necessarily. And then I don't think this is true either. It just depends on the density, not just mass or size. Let's go. To the left, to the left, to the left, to the left. For temp, low temp, increase in the pH, and I think and I think CO2. The right is going to be decrease in the pH, higher temp. Actually, technically, wasn't this CO? And I think to the right it's going to be 2, 3, 2, 3 dpg. And I think this is actually also increase in CO2, if I'm not mistaken. So no. Unless I'm wrong. I could be wrong though. We want it to the left. Oh, okay, look, an increase. So, I think it was an increase in CO2. Anyways, an increase in the pH for sure. That's what we just said. I guess increase in T3BG, right? But a decrease would just be normal. It would just be normal. So increase in pH for sure. CO, low temp. So not increase in temp. Increase in carbon dioxide, we go to the right. And increase BPT, we go to the right as well. So pH. What was hematocrit again? What does that mean? Oh, I think it was that serum, right? An increase in the serum. I don't remember what hematocrit means. Hemolysis, maybe? Okay. Iron deficiency? I don't know. What are we talking about here? Oh, that one. Oh, what's that? I forgot. Gotcha. Yes, sir. Well, we know that It's pretty bad. Is it like that? Something like that, right? And we have, I don't know, let's think 100. So I don't think so. This one, maybe? I don't think so, though. Oh, but maybe this one actually, potentially as well, right? I don't think so. Well, they're both saying high CO2. And as you know from last time, if we increase our CO2, we're going to go shift it to the right. Which means that isn't it high O2 would increase the I think C. I'm thinking more C. I don't know why. High O2 reduces euthermia. I don't know if that's true though. I don't really know if that's true. I don't think that's true either. I don't know. I think C. Oh, so it wasn't C. So I think then it was B, huh? Ah. Let's see, it says for CO2. Oh, yes, that's true. Oh, right. That's the only one. Okay, yeah. Yeah. Well, we know it was CO2 plus H2O turns into HCO3 minus, which turns into plus H plus, right? And it can also go backwards. But that means we're increasing CO2 here. I guess in this way we have decreased CO2. Decrease CO2 and there's high O2. How do we increase this one? Increase the CO2. So that means that we decrease O2. Do we want to go Haldane effect here for sure? Increase oxygen affinity by binding with free proteins. Potentially, maybe. That means, hold on, let me see what that means. Um, that means we have a low pH. But low pH makes us get a right shift. Does that increase oxygen binding affinity? No, I believe that lowers binding affinity. So it's not going to be D. Decrease oxygen affinity by binding with free protons? Yeah, but I just don't think that gets us. I don't see how that gets us. Wait, maybe. Decrease oxygen affinity. I just don't see that either. I don't think that's true. Anyways, the purpose here would be to increase O2 binding. We'll increase O2 binding. If we increase O2 binding, oh wait a minute. Yeah, if we decrease O2 binding, we're passing the O2 to the cells, right? That's if we decrease O2 binding. So if we want to get more bicarbonate, we would increase O2 affinity. Increase O2 affinity. So actually, I mean, decrease. If we increase O2 binding or O2 affinity, oh wait, hold on, maybe I'm thinking about it wrong. Let's restart. Like increase in bicarbonate. What am I thinking about, eh? Jesus. If we increase in bicarbonate, means we have high CO2. That's a right shift, essentially, because we're also increasing the H plus. The H plus, we're lowering the pH. So I think this is your classic right shift. Not your classic right shift right there, basically. That's going to allow decrease H3 can bind directly with hemoglobin though. Actually, I think it said it could, right? No, I think these two can. I don't think this can. Yeah, anyways, I think that's gonna decrease binding O2 binding. I don't think you can directly bind with hemoglobin, but yeah, it would be a decrease. Actually, I'm going with C on this one. You guys let me know if I'm right or wrong and why. But I think C because if we have an increase in bicarbonate, which is the weak acid, going to dissociate into HCO2 and free protons. So we have a lot of free protons. These two molecules, or this molecule and this proton cation, proton will and can bind. And if it can bind, that's going to decrease O2 affinity based on the I think based on the right shift curve, right? Which is this one here. So we now need well, I don't know. Is that yeah, well, something like that. Anyways, yeah, I think it's C. Let's go with it. Oh no! Oh no! Oh no! Increase it to running thing. I don't think it's gonna. I don't think it's gonna increase it. Pretty sure it's going to decrease it. Well, I don't know if it's saying that this is gonna bind with 3 protons, or that the hemoglobin is gonna bind. It's the hemoglobin that's gonna bind. Well, I don't know. Okay. What the heck? I was wrong. I was completely wrong. I thought that would be right. It's getting hot. Seriously? Seriously? Increase O2 binding. What the heck? What the heck happened? What the heck happened? Why? You think D? Yeah, it's hot out here, dude. It's hot. It's almost 90 degrees Fahrenheit right now. I'm like, I don't know how I'm not sweating, but well, it's because I got a little bit more like gym clothes. I got the fan right next to me. Okay, D. Wait, you said D. You think C? I think C. GG go next class. Uh, I was wrong. Let's see what happened. It's basic. Well, it is what it is. Everyone struggles different points, right? I can't read it. In the red blood cells, water. Yes. Huh? Yeah, that's literally what happens. H plus binds hemoglobin, which decreases the affinity for oxygen. A low pH decreases oxygen affinity. What? C is correct. It literally says so right here. The reaction form is reversible. Whoa, reaction to form hydrogen. Yes, I know. Buffer the free. Oh, they got me. I wasn't thinking about Lashley's principle here. Wow. Here's another. Would buffer the free hydrogen and thereby increase the pH of the blood. Wow, what a question, huh? Any Houston bicarbonate. Increase. To compensate for low oxygen affinity, you have to bind it with free protons. Okay, yeah, sure. Okay, yeah, I guess. Well, when would you know to use Lashley's principles? Is it all the time? How would you know? Is it every time? And I got my understanding was correct, but then I just didn't account for Lashley's. Lashley's would buffer the free hydrogen. How would that increase the pH of the blood? Got me. They have both the antibodies for A and B, eh? Wait. Present in the plasma. Yeah. Yeah, the plasma contains. Well, actually. Well, it's not B, it's not D. It's either A or C. It has both. Um, 11. Um, I'm gonna go with 10. I got it wrong here. I'm gonna go with 10 though. Let's go. Let's go. Drawing's correct. Look at that. Perfect, beautiful drawing. Woohoo! Um, oh. Oh. 8 and 10. Last one. I don't know what the heck is that. Oh, okay. Well, this starts first, so I don't think this is part of the intrinsic. So I don't think it's going to be 8 because that'd be much earlier. 12 and 10. Why did I say 8 and 10 here? What the heck? 12 and 10. I mean, technically D, right? We'll go A first, and then D, and then B, and I don't know what C is. I don't know. But I think go in this order. But that just happens all the time. I think D, right? I don't know. Ugh. Into a component. I think then it's talking about factors. Let's go with B. Oh, need something? Okay. Oh, plasma. Okay. Okay. Already in the blood. Oh, okay. That's what it's trying to say. Yeah, that makes sense. Whoops. Definitely not. So we're looking for a false. So right. Thymus or kidney? Maybe kidney? Definitely not A and B. Thymus. Potentially could be the thymus, huh? Potentially. And the kidney? Production. I don't know. Let's go with the kidney. Ooh, the thymus. Wrong guess, buddy. The kidney secretes erythropoietin. Ah. Oh, I forgot about the hormone. Yeah. Ah. Myeloid. Macrophages. Lymphoid is B cells here, I think. And T cells. And the other stuff, whatever. So let's see. What do we get with just that? Potentially. That was okay. Ah. Oh dang, the shower line. Someone Street the pathway. You're funny, George. You're funny, man. Funny, man. Broken capillary vessels. Exactly, it's the percentage. I think it's fibrin. I think it's fibrin. Oh, let's go. Damaged bone marrow would be a non-functional spleen would be genetic syndrome. I don't know. Excess clotting would be genetic syndrome. Seriously? Damaged bone marrow. Damaged bone marrow. I thought excess clotting would lower the platelet count because platelets are used for clotting. Damaged bone marrow. Erythrocytes are created in the bone marrow, so the ends, right? The ends of it, at the ends of the bones. The spleen, though, I thought the spleen has the monocytes, and it's responsible for filtering out, or I guess recycling, right? Recycling the old blood cells and using up that nutrients. Well, yeah, using up the nutrients. So, genetic syndrome. I don't even know what it means by that. Yeah, you got me. I'm not sure. Oh, okay. Oh, and platelets, and platelets. I didn't know if it was just, I thought it was just red blood cells. Okay, so it's and platelets as well. I didn't know that. One patient with low platelets counts have chemo. Petechia, broken capillaries. Well, right. I don't think this makes sense. This makes sense. If there's decreased repair, if the platelets can't repair the blood vessel or clot it, then it's going to be rushing out, right? And that's what the visible spots are on your skin. Obstruction of small blood vessels. Increased obstruction. I think that'd be the opposite. Increased damage. I mean, potentially. I'm not sure, but I'm thinking D or D. Let's go with D. Okay. There are more patients between 20 and 30. That's wrong. I don't think so. 20,000. Oh, wait. Among patients, there are more patients with platelet count of 2030. Yeah, that's true, because platelet count below 50 is low platelet count. If you have a platelet count of 10K, 50%, that's not true. That's just the percentage of the people with it. The greatest increase in risk of beginner occurs between 20, no, it occurs between anything less than 10,000. You have a higher chance on that would be. What? The greatest risk, 10 to 20K. Between 20 to 30K. 20 to 30K. 20 to 30K. And 10 to 20K. Oh, maybe if we subtract those numbers, right? 55. 55 minus 15. 55 minus 15 is is 40, and between 10, 81 minus 55. Oh, it's 40 here. Oh, I guess so. Actually, maybe that might be D. Yeah. The rate jumps from 12% to 55%. Oh, yeah. Oh, okay. Yeah, sure. Well, that's what I was doing too, actually. Which is significant. Well, yeah, that's fine. All right, well, it is what it is. Nice. Let's take a 10-minute here before we begin the next one. Kind of reset. Let's see, 10. I'm just thinking these are all 10. Just about, huh? 58, 8, and then the rest. Yeah, it's fine. We have time. We can take a break. We'll do better next time. I think just being able to learn is more valuable than just trying to get the right answer, right? If I don't know it right away, then that's okay. It's the first time I'm thinking about things like this, so it's okay, you know. I mean, between now and when I officially become a doctor is quite a long time, like 8+ years, so potentially. So I'm just starting. I think it's okay if I get some wrong, you know. Okay, let's take a break. I'll be right back. Okay, anyways, we got some watermelon. Okay. Or, yeah.
Cardiovascular system. Here's a cartoon of it, and we have our heart, which is the pump, which pumps blood through the blood vessels round and round through the body. And the purpose of this whole system is to get blood out here to the capillary beds. So here's a capillary bed, and that's where the blood vessels become very skinny, and they divide. And because they're so skinny, they have a lot more surface area. And that increased surface area allows the blood to exchange its oxygen and nutrients with these cells here that I'm drawing, which need those things. So the blood gives its oxygen to these cells, and by the time it gets through the capillary bed, it's lost its own oxygen. So now it's blue, and that blood goes back to the heart. Now I haven't drawn it, but here also the blood goes through the lungs and gets new oxygen so that when it goes around again, it has oxygen. So this is a closed loop with blood going round and round and round. But it has a problem, which is that the heart needs to pump quite strong for blood to go around fast enough to feed all the cells in your body. And what that means is that the pressure that the heart exerts is very high. So there's high pressure in the heart, and there's high pressure throughout these blood vessels. And what that actually does is it forces some fluid out of your blood vessels, and especially out of these capillaries here. It forces some fluid out, and that fluid is not exactly blood, because, for example, the red blood cells, which are in your blood, are too big to squeeze out. But the sort of more liquidy part of your, which are in your blood, are too big to squeeze out. Because, for example, the red blood cells, which are in your blood, are too big to squeeze out. But the sort of more liquidy part of your blood, which is like the plasma, that does get squeezed out. And so that's what ends up here. And that fluid mixes in with the cells which are outside of the capillaries, and it accumulates. Now this is a problem, because if we let this go on, we would lose pretty much all of the fluid in the blood, and we would get a buildup of fluid out here, and that would be an unsustainable situation. So that's where your lymphatic system comes in. This is the problem that it addresses. So your lymphatic system is actually another plumbing system, which I'm going to try to draw here. So it's another plumbing system. It has these vessels which kind of start in the middle of nowhere, and they collect this fluid. The fluid goes in, they collect it, and they bring it back into circulation. So they bring it back into the blood. And that way, it goes back in, and the blood can continue to circulate, and we now do have a sustainable situation. So these vessels here we call lymphatic vessels. And if you'll notice, they're a little bit different from blood vessels because they don't form a closed loop. The lymph, as this stuff is called, lymph, so that's the fluid that gets forced out of your blood. The lymph goes in here, and it gets dumped out into the blood vessels there. It doesn't go back around to the start. So that's kind of the basic explanation for why we need these lymphatic vessels. But to give it a little bit more depth to circulation, so they bring it back into the blood. And that way, it goes back in, and the blood can continue to circulate, and we now do have a sustainable situation. So these vessels here we call lymphatic vessels. And if you'll notice, they're a little bit different from blood vessels because they don't form a closed loop. The lymph, as this stuff is called, lymph, so that's the fluid that gets forced out of your blood. The lymph goes in here, and it gets dumped out into the blood vessels there. It doesn't go back around to the start. So that's kind of the basic explanation for why we need these lymphatic vessels. But to give it a little bit more depth, let's take one of these capillaries, and we're going to zoom in, and we're going to draw it a little bit rotated here. Hope that doesn't throw you off. These are the endothelial cells lining that capillary. And we're going to study exactly how fluid gets forced out. So as we move along this capillary, the blood is going to become deoxygenated, and so I'm drawing the changing colors, even though, in reality, it's not the endothelial cells that are changing colors, but having these colors will help orient, I think. And so flowing through this capillary, you have little red blood cells, which I'll try to draw as little discs there. You have little red blood cells, and of course you have lots of water, a lot of water. And finally, you also have a bunch of little proteins. Some of the proteins are actually bigger than others, so we'll draw them in varying sizes. But all this stuff is present in the blood. And because of the high pressure, it gets squeezed out. So the first question is exactly where and how does it get squeezed out? And the answer is it gets through between the cells. The cells are not quite held together tightly enough to prevent stuff from getting out. But they are held tightly enough to prevent the bigger things from getting out. So the red blood cells and the bigger proteins won't get out. But what will get out is some of the fluid, some of the water, and some of the smaller proteins, which we'll draw like this. So actually, by the time the blood gets down to the latter part of the capillary, it's lost some of these smaller proteins and some of this fluid. And so let's show that by actually erasing some of it. And so the concentration of bigger proteins is higher. And you could even say that the concentration of red blood cells is a little higher. Higher concentration of solutes of the capillary than we had over there. And the reason why I'm mentioning this is because there's actually a subtlety, a complication here, which is that although lymph, or what will soon be lymph, is being forced out of the capillary over here, a little bit more depth. Let's take one of these capillaries and we're going to zoom in and we're going to draw it a little bit rotated here so that doesn't throw you off. These are the endothelial cells lining that capillary. And we're going to study exactly how fluid gets forced out. So as we move along this capillary, the blood is going to become deoxygenated, and so I'm drawing the changing colors, even though, in reality, it's not the endothelial cells that are changing colors, but having these colors will help orient, I think. And so flowing through this capillary, you have little red blood cells, which I'll try to draw as little discs there. You have little red blood cells, and of course you have lots of water, a lot of water. And finally, you also have a bunch of little proteins. Some of the proteins are actually bigger than others, so we'll draw them in varying sizes. But all this stuff is present in the blood. And because of the high pressure, it gets squeezed out. So the first question is exactly where and how does it get squeezed out? And the answer is it gets through between the cells. The cells are not quite held together tightly enough to prevent stuff from getting out. But they are held tightly enough to prevent the bigger things from getting out. So the red blood cells and the bigger proteins won't get out. But what will get out is some of the fluid, some of the water, and some of the smaller proteins, which we'll draw like this. So actually, by the time the blood gets down to the latter part of the capillary, it's lost some of these smaller proteins and some of this fluid. And so let's show that by actually erasing some of it. And so the concentration of bigger proteins is higher. And you could even say that the concentration of red blood cells is a little higher. So we have a higher concentration of solutes in this part of the capillary than we had over there. And the reason why I'm mentioning this is because there's actually a subtlety, a complication here, which is that although lymph, or what will soon be lymph, is being forced out of the capillary over here, actually some fluid comes back into the blood vessel over here. And to understand that, you need to know that the concentration of solutes is higher here, which leads to a higher osmotic pressure pulling fluid back in. And to understand that, you also need to know that the pressure, the regular hydrostatic pressure, is lower in the latter part of the capillary compared to the earlier part. So the pressure goes down. And the pressure what was pushing the lymph out of the blood vessel over here. So now we have less pushing out and more pulling back in. And the stuff that's pulling back in is the osmotic pressure caused by the increased concentration. So here, some of the fluid and some of the smaller proteins might get pulled back in. So now you might be confused because I said that fluid is getting pushed out, is leaking out of the blood vessels. And here I'm saying that's leaking out but then coming back in. But the fact is that more goes out then comes back in. So let's draw these arrows a little bigger. So more goes out then comes back in. And so net result of the blood traveling through this capillary is that you end up with lymph squeezed out. So now you know a little more detail about how and why we end up with lymph. But you might be asking yourself, why don't these cells just tighten up their connections there to prevent stuff from getting out? But the answer is you have to remember that we have other cells around here which want to be fed. They want to get glucose and other such things from the blood. And so it's important that little glucose molecules and small proteins like hormones can get out into the space near these cells so that it can interact with them. So basically, if these endothelial cells in the capillaries were tightly connected together, then all these cells in your body would kind of be sealed off. And you might be wondering, well, are these gaps also necessary so that oxygen can get to the cells? And actually, oxygen is different. It's very small. It's just 2 atoms, 1 molecule. So oxygen can just go right through the cells. It can just travel right through walls and get where it needs to. So hopefully this gives you a better idea of how lymph is kind of formed from capillaries, how a bunch is squeezed out and only some of it gets back in. So finally, I just wanted to draw a pretty ugly human being and make the point that you pretty much have capillaries all over your body. They're feeding all your muscles, all your different tissues. And for that reason, you need lymph vessels to take lymph away from pretty much all of your body. So you have lymph vessels coming out of your legs, coming out of your arms, and so on. And in a sense, they have a similar structure to blood vessels, which is that they start very small, and many of them come together and join up into a bigger lymph vessel, and that lymph vessel joins with another bigger lymph vessel, and so on. And so it's kind of like they start out as capillaries, and then they merge together and get bigger and bigger. Of course, they have the big difference for blood vessels, which is that they're not a closed loop. Ultimately, when they've consolidated into big lymphatic vessels, they just dump their contents back into blood circulation. Big lymphatic vessels, they just dump their contents back into blood circulation. The heart pumps blood throughout the body, and it pumps so powerfully that it actually squeezes some fluid out of the capillaries. And that fluid becomes lymph. And it's the lymphatic system that gathers all that fluid and brings it back into circulation. But this idea might bother you. You might have an objection, which is these lymph vessels don't have a heart of their own. I didn't draw one, and it's because they don't have one. So how is it that they're able to pump this fluid in one direction? And moreover, how is it that they're able to pump it back into this high pressure system? Given that they don't have a pump, that must be quite difficult. There are two answers to this question, really, and the first is a little simpler, so let's start there. The first answer is essentially in the location of re-entry. So the reason why lymph is able to get back into the high pressure system is because lymph is quite intelligent about where it tries to re-enter the high pressure system. So I'm drawing a star here because that's where the lymph re-enters. I didn't draw that by accident. It re-enters at the very end of the venous circulation system. And the pressure there is much lower than the pressure in the arteries and even the pressure in the capillaries. The numbers are actually pretty striking. The pressure here in the early arteries can be about 120 millimeters of mercury. That's kind of like your average blood pressure. But over here, just before it enters the heart, the pressure is more like 5 millimeters of mercury. So the fact that the lymph fluid enters circulation at the end here makes it much easier. It has to fight against much less. If the lymph vessels ended up trying to drain here, let's say into the aorta or into a big artery, probably none of this would work. So that makes the job easier, but it doesn't explain how lymph moves sort of one directionally into the blood vessels. What is actually forcing the lymph? What is getting it to move in this direction? Why wouldn't it just come back as much as it would go forward? And the reason why that's not the case is because of valves. So valves are structures within the lymph vessels which prevent fluid from going back. So let's draw a lymph vessel here. And a valve might look something like this. And what this valve accomplishes is that if fluid gets pushed that way, it'll part the two leaves of the valve and it'll get through. But let's say that fluid tries to come back. When it tries to come back, it'll push the valves back, the leaves of the valve back together, and it'll create an obstacle. Now, this is a really smart system, and actually, it's not only used in your lymph vessels. You might know that it's also used actually in the heart. You have 4 big valves in the heart that operate on this exact principle. And it's also used in veins because the pressure to push fluid through veins is sometimes not sufficient. And so having a mechanism to prevent backward flow is very helpful. But still, you might not be satisfied because you might say, well, what causes the lymph to move at all here? Why wouldn't it just sit where it is? And there are actually 2 ways that the motion begins. One is that you actually have a little bit of smooth muscle attached to your lymphatic vessels, and that can contract. And just by squeezing, it'll cause motion of the fluid forwards. So that's the first mechanism by which the motion starts. And the second is skeletal muscle. skeletal muscle just refers to basically all the big muscles in your body that are under voluntary control. Think about your leg muscles, your arm muscles, and so on. And the reason why this does something is that just throughout the course of your average day, you use your muscles, you move around, you have a certain amount of jostling in your body. And so it's inevitable that you're going to squeeze certain parts of your body at some times. And when you squeeze a part of the body that has a lymph vessel like this, it's going to start the motion. It's going to squeeze it just like the smooth muscle did. And you'll get fluid moving ahead in the direction that the valves allow them to. And so in addition to the valves, which we can draw in to our diagram here, in addition to those, there's an interesting contraption where the lymph first enters the lymphatic vessels. So I drew it here as an open tube, but in reality, it's closed. At least it looks closed, but it's porous, of course, and that's what allows fluid to get in. Let me just draw this a little bigger. But basically, this is where the lymph vessel starts, and the walls of this lymph vessel are kind of like valves in and of themselves, in that they allow fluid to come in. But when the pressure inside rises, it prevents fluid from going out. So the lymph cannot go back out. So finally, let's just look at a human body to get a sense of where everything, they allow fluid to come in, but when the pressure inside rises, it prevents fluid from going out. So the lymph cannot go back out. So finally, let's just look at a human body to get a sense of where everything that we're doing fits in. So here's another ugly human. Let's quickly give him some arms, a head. And now we can actually show where the lymph re-enters circulation. So let's say that that's the heart. Well, you probably know that one of the huge veins leading into the heart is the superior vena cava. And right near the superior vena cava, you have what are called the subclavian veins. And you have one on the right and one on the left. They're called subclavian veins because they pass just under the clavicle. And it's actually right into these that the lymph is re-entered. So I'm drawing that in green so that it corresponds with that. It's at this point that we have very low pressure, and it's there that all the lymph from the body goes. So that includes lymph from down, is the lymph re-enters circulation. So let's say that that's the heart. Well, you probably know that one of the huge veins leading into the heart is the superior vena cava. And right near the superior vena cava, you have what are called the subclavian veins. And you have one on the right and one on the left. They're called subclavian veins because they pass just under the clavicle. And it's actually right into these that the lymph is re-entered. So I'm drawing that in green so that it corresponds with that. It's at this point that we have very low pressure, and it's there that all the lymph from the body goes. So that includes lymph from down in your legs, and from your arms, and from your neck, and so on. And it's pretty remarkable if you think about it, that they pass just under the clavicle. And it's actually right into these that the lymph is re-entered. So I'm drawing that in green so that it corresponds with that. It's at this point that we have very low pressure, and it's there that all the lymph from the body goes. So that includes lymph from down in your legs, and from your arms, and from your neck, and so on. And it's pretty remarkable if you think about it, that all the lymph in your body traveled up this entire path and got dumped back into circulation there, and all of it was without an active pump. It was all done through this method of a little bit of squeezing with smooth muscle, but mostly just the ingenuity of these one-way valves that take advantage of the fact that you're always moving around to sort of squirt the lymph back up all the way up your body to essentially your neck.
Right.
We've talked about how the purpose of the lymphatic system is to collect fluid that's squeezed out of blood vessels like this one, to collect that fluid and eventually bring it back into the blood so that we don't lose too much fluid. So this is a blood vessel, and around it we have some cells that are maybe being fed by that blood vessel. And at the same time, we have these lymphatic vessels that kind of start out of nothing, and they're porous so that they can collect the fluid that was squeezed out of the blood vessels, and then eventually they'll put that fluid back into the blood. But the lymphatic system actually has other purposes. It helps us. We've talked about how the purpose of the lymphatic system is to collect fluid that's squeezed out of blood vessels like this one, to collect that fluid and eventually bring it back into the blood so that we don't lose too much fluid. So this is a blood vessel, and around it we have some cells that are maybe being fed by that blood vessel. And at the same time, we have these lymphatic vessels that kind of start out of nothing so that we don't lose too much fluid. So this is a blood vessel, and around it we have some cells that are maybe being fed by that blood vessel. And at the same time, we have these lymphatic vessels that kind of start out of nothing, and they're porous so that they can collect the fluid that was squeezed out of the blood vessels, and then eventually they'll put that fluid back into the blood. But the lymphatic system actually has other purposes. It helps us in other ways, and we're going to talk about one of those other ways in this video. And to talk about that, we need to talk a little bit about infection. So infection is when your body gets attacked by a foreign invader, and that invader will usually be a bacteria or a virus. And in this case, let's talk about a bacteria. So let's say we get a bacteria that invades this tissue here. So the first thing you might ask is, why am I drawing the bacteria here? Why am I drawing it outside of the blood? Maybe I should be drawing it here inside the blood. And one reason why, I might think that, why you might think that, is because think about when you get infected. Sometimes you get infected when you cut yourself, right? When you cut yourself, you might get an infected wound. And when you cut yourself, you see blood. So you might think that you're getting infected because bacteria or viruses or whatever are getting into the blood. But actually, that's not quite true. Infections are usually not in the blood. And actually, there's a pretty simple, you could say, proof of that, which is that when you get infected, infections almost always stay localized. And by that, I mean that they usually stay in one place. So think about when you get an infected cut, usually, let's say it's on your finger, the infection will stay on your finger. Or let's say you get a UTI, which is a urinary tract infection. The infection usually stays in your urinary tract. Or maybe you get pneumonia, the infection stays in your lungs. So if the infection was actually in your blood, it would immediately go all over the body. And that does happen sometimes, but it's way more serious than the majority of infections. So really the most accurate way to draw a typical infection is to draw the infection occurring in the tissues. Now, when we have this infection, there are going to be some local immune cells that your body has that's going to be fighting these bacteria and trying to kill them. But your body also has more powerful defenses, which consist of B cells and T cells. And these guys are part of the adaptive immune system, which means that they actually sort of react to the specific invader that's there. So unlike these guys here, which for the most part are macrophages, unlike these macrophages who can fight, lots of different kinds of bacteria, these B cells and T cells will react to the specific bacteria and end up having a much more powerful effect against them because of that. They're specially tailored to the invader. But the problem is that these guys don't just sit out there in the tissues where the infections start. And there are a few reasons for that, but probably the most important is that for these B and T cells to specialize against these invaders requires a very complex process that couldn't possibly occur just willy-nilly out here in the tissues. They require a special environment, which we can draw out here, which is kind of like a training camp where they can develop in response to the specific invader. But now we're faced with a problem because we've already said that these bacteria stay here in the tissues. They're not swept into the blood and then carried to the B and T cells over there. They stay in the tissues. And these B and T cells are not out there in the tissues. So how can we get these B and T cells to see these bacteria and be able to react against them? And that is precisely what this lymphatic system does, because these bacteria are going to get but your body also has more powerful defenses, which consist of B cells and T cells. And these guys are part of the adaptive immune system, which means that they actually sort of react to the specific invader that's there. So unlike these guys here, which for the most part are macrophages, unlike these macrophages who can fight, lots of different kinds of bacteria, these B cells and T cells will react to the specific bacteria and end up having a much more powerful effect against them because of that. They're specially tailored to the invader. But the problem is that these guys don't just sit out there in the tissues where the infections start. And there are a few reasons for that, but probably the most important is that for these B and T cells to specialize against these invaders requires a very complex process that couldn't possibly occur just willy-nilly out here in the tissues. They require a special environment, which we can draw out here, which is kind of like a training camp where they can develop in response to the specific invader. But now we're faced with the problem because we've already said that these bacteria stay here in the tissues. They're not swept into the blood and then carried to the B and T cells over there. They stay in the tissues, and these B and T cells are not out there in the tissues. So how can we get these B and T cells to see these bacteria and be able to react against them? And that is precisely what this lymphatic system does, because these bacteria are going to get swept in. And at the same time, these macrophages might gobble up some of these bacteria. And once they've done that, they might migrate into these lymphatic vessels. And it turns out that the way your body resolves all this is to sweep all these things directly to the nearest lymph node. And that's what this structure is called. It's called a lymph node. Lymph node. It's called a node because it's generally a smallish object in your body, and it looks somewhat circular, so it's like a node. And the word lymph has to do with the fact that we have B and T cells here. And it's also convenient because what leads to it is the lymphatic vessel. So these bacteria and some of these macrophages carrying the bacteria will get swept along, and they'll be in contact with these B and T cells who can then multiply and specialize and get ready to fight this infection over here. And we're not going to talk about how they ultimately do that because that's a topic really for another video. But I just wanted to mention that, as we said, the primary purpose really of the lymphatic system, of these lymphatic vessels, is to carry fluid back into the blood. So obviously, by the time all this stuff gets here to this lymph node, that can't be the end of the lymph vessel. So the lymph vessel is actually going to continue. It's going to continue, and it's going to eventually carry fluid and such back into the blood. So ultimately, the fluid is going to end up back in the blood. And so actually another nice side effect of having these lymph nodes here interspersed throughout the lymphatic vessels is that they'll actually filter all this fluid that's going to get put back into the blood. If you didn't have this lymph node here, you would still need the lymphatic vessels to get rid of the fluid that your blood is filtering. And what would happen is these bacteria would get just put directly back into the bloodstream. And that would be a problem because, as we said, infections of the blood are way more serious than local infections of tissues. So this lymph node acts as a filter for the lymph, which is passing through here. And it filters, actually, it also has some macrophages here that are going to help gobble up some of the bacteria that might be floating through. And so in sum, I think we're left with something that's really a very elegant system. What happens is we've developed a way to sweep all these bacterial invaders basically to the nearest police station. And at the same time, we've developed a system to filter the fluid that got squeezed out of these blood vessels, to filter it as it passes through here, so that by the time it gets to the end, it's free of bacteria and other debris. So before we finish, let's talk a little bit more about these lymph nodes so we have a sense of what they're like in reality. So they're generally fairly small. They're definitely much smaller than your average organ, and so they're not considered organs. They're about 1 to 25 millimeters, and they're small enough that you can have lots of them in your body. And so you have about 600. There are about 600 in the body, and some of them are located close enough to the skin that you can feel them. And those would obviously be the bigger ones. It would be hard to feel something that's 1 millimeter. And so let's look at where some of these are located on a human body. Let's actually give this guy a neck to be generous. So the lymph nodes are obviously located all along lymph vessels, but because there's 600 of them, they're located along the larger lymphatic vessels that have already collected many of the little lymphatic vessels and consolidated them. So let's start with places where you might actually feel lymph nodes on your own body. So often you can feel the lymph nodes that are in the inguinal region there, kind of between your thigh and your abdomen. And as we know, there are kind of large lymphatic vessels that consolidate here and merge and rise up the body. And all along here, you might have lymph nodes all along there. And then often when a doctor gives you a checkup, he'll feel for lymph nodes along your clavicles there. He might feel along your neck, and he might actually feel on your face and below your jaw. So all those are along lymph vessels that are coming down. And then the lymph vessels that are coming here from your arms, those will have lymph nodes along them. And so in this way, you kind of have about 600 of these lymph nodes sprinkled about in your body. And the cool fact to remember is that any lymph that's coming out of any tissue in your body will pass through at least 1 lymph node before it goes back to your blood. So even if it's out in your little pinky finger or something, the lymph vessels that carry that back will come and join a larger lymph vessel, which will pass through a lymph node. Or even if it's here in your stomach, it'll come and it'll join and it'll pass and it'll get into a larger one with a lymph node. So really all the lymph that goes back into your blood is filtered.
That's pretty cool.
So, 'cause, 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 ' We've already talked about two purposes of the lymphatic system. The first was to bring the fluid that was squeezed out of the capillaries back into the blood. And the second was to help out the immune system. But there's one more, there's a third, and that we've already talked about two purposes of the lymphatic system. The first was to bring the fluid that was squeezed out of the capillaries back into the blood. And the second was to help out the immune system. But there's one more, there's a third, and that's what we're going to talk about in this video. So let's look at we've already talked about two purposes of the lymphatic system. The first was to bring the fluid that was squeezed out of the capillaries back into the blood. And the second was to help out the immune system. But there's one more, there's a third, and that's what we're going to talk about in this video. So let's look at a piece of the small intestine. Now, obviously, the small intestine carries bits of food that your body wants to absorb and use for energy. So one of the most important elements of that food is little glucose molecules, which are absorbed and are used as the primary source of energy for the body. So actually, since it'll be helpful for us, let's at least make this two-dimensional. So let's look at some cells here of the small intestine. So these are cells lining the small intestine. And the way that glucose is actually absorbed by your body is that it's pumped into these cells here, the cells lining the intestine, and then it's pumped out of them. And then once it's here in this space, it's able to diffuse into capillaries which are nearby. So it'll diffuse into the capillaries, and once it's there, it can go and spread out over the whole body and feed various cells. But glucose is not the only thing which needs to be absorbed in your small intestine. And actually another compound is fat. So fatty acids, which are floating around in your small intestine, need to be absorbed as well. And the structure of these things, to remind you, looks something like this. You've got this carboxylic acid group attached to a long chain of carbons. Now, like glucose, these guys are taken up by these cells in the intestine, but when they're put out by those cells, they no longer look like this. By the time they're put out, they're packaged into these actually rather large spherical objects, which have a weird name. It's chylomicron. So they're packaged into these spherical things called chylomicrons. And these chylomicrons are useful for holding a lot of these fats together. But they have a problem, which is that chylomicrons, as you might guess, are too big to diffuse into the capillaries. So they can't do that.
Okay.
But you don't want to have chylomicrons just accumulating here in your intestine. You want to spread them out to the body where they're needed. And so that's where our good friend, the lymphatic system, comes in. So we have these lymphatic vessels nearby that are much easier to enter than the capillaries. And the chylomicrons are able to diffuse into these vessels and be transported through the lymphatic system and eventually emptied into the blood circulation so that they can spread throughout the body. Because this is such an important process, these lymphatic vessels in your small intestine are given a special name, and that name is lacteal. So the lymphatic vessels in your small intestine are known as lacteals, and those are the ones that take up your fats in the form of chylomicrons. So here we have our third important function of the lymphatic system, which is to transport things which didn't originally come from the blood, to transport them into the blood. And we can sort of generalize it a little bit and say that, maybe a little further away from the small intestine, somewhere else, you have some cells that are hanging out. And actually, there are some other things which your body might want to put into lymphatic circulation. So you may have some cells here or elsewhere in the body that are producing maybe some proteins like hormones, or maybe some waste products. And in some cases, those proteins might have trouble getting into the capillaries, and these waste products also might have trouble. But you want these things to get into the blood because, for example, for hormones, you want them to be able to travel throughout the body and have their effects on the tissues that they're supposed to affect. And for waste products, you want them to be able to get into the blood and eventually get to the liver where they might be broken down, or to the kidney where they can be excreted. So in those cases, you have this secondary system of getting these things into blood circulation through the lymphatic vessels. So these are proteins and wastes. And the reason that we're talking about these at the same time as chylomicrons is because these are all things that don't actually come from the blood, but we want to put them in the blood, and we can't do it directly. So we put them into lymphatic circulation first. So now that we've learned about the third purpose of the lymphatic system, it might be a good time to review all three purposes at once. So why don't you pause the video and see if you can remind yourself of all three. Otherwise, I'll go ahead and describe them here.
Okay. Second one was to pick up bacteria, macrophages, and also filter debris and others. And also just filter it out. And then now I guess it's also for lipid and protein transports.
So the first purpose of the lymphatic system, let's draw another lymphatic vessel here. The first purpose was to collect all the fluid which was forced out of the capillaries by the high pressure that's present in the blood, to gather all that fluid and bring it back into blood circulation via the lymphatic vessels so that you don't have too much fluid accumulating here in the tissues. So that's the first purpose. This is just fluid with maybe some small plasma proteins, but not with any red blood cells or anything like that. The second purpose had to do mostly with infection. So if you have some bacteria infecting some tissue in your body, the lymphatic system basically offers a way to bring those bacteria to the attention of your immune system. And they do that by basically taking them up and bringing them to the nearest lymph node. So that's a lymph node, and that is where your B cells and T cells are hanging out. So that's the second purpose right there, the second purpose of your lymphatic system. And the third purpose, of course, is what we discussed today. It's transporting other things such as chylomicrons or other proteins or wastes, transporting them into the blood when they have trouble simply getting into capillaries the normal way.
This guy is pretty to the point. You don't.
So we've talked a lot about the lymphatic system, and in this video I wanted to talk more about lymph, which is the fluid that's in the lymphatic system. So we know that lymph comes from blood vessels originally. It's the fluid that's kind of squeezed. So we've talked a lot about the lymphatic system, and in this video I wanted to talk more about lymph, which is the fluid that's in the lymphatic system. So we know that lymph comes from blood vessels originally. It's the fluid that's kind of squeezed out of blood vessels. And so here, let's say this is a capillary. I'm drawing the endothelial cells around the capillary. So lymph is what comes out of here, what's squeezed out through the little holes between the capillaries. And just so we have our terminology straight, really lymph is only called lymph once it gets into the lymphatic vessels. So once this fluid gets into here, now we can actually call it lymph. But before it does, it has more, it's more called extracellular fluid because it's outside the cells that are out here. But really the composition is the same, and so this is just a semantics thing. But so in this video, let's try to figure out exactly what lymph is made of. And so to do that, let's start with blood, because lymph originally comes from there. So in blood, we obviously have red blood cells. So let's draw a couple of those in here. These are red blood cells. And in reality, we should draw more than a couple, because we know that blood is actually consisting of about 40 or maybe even 45% red blood cells, 45% by volume. And that's in the average person. If you're anemic, it'll be less. So blood has about 40%. We're drawing much less than that here, but it's kind of hard to draw them all packed in, so let's leave it like that. And so other than that, of course, we have water, which we'll draw white. This is water. And we also have proteins and we'll draw those of varying sizes because proteins really do vary by size, and we have many different kinds of proteins in the blood that do many different kinds of things. And that's all that we'll draw here. Even though there are also glucose molecules and fats and other things in the blood, we can ignore those for now. So what gets out here? What manages to squeeze through? Well, we know that the red blood cells don't manage to squeeze through. So certainly by the time we get to extracellular fluid, we'll have 0% red blood cells. And so lymph will have no red blood cells. But other than that, let me ask you a question. Do you think that lymph has more protein or less protein than blood?
It's a good question.
By concentration. So it's actually
It's a good question. I mean, it depends. Smaller proteins, probably, and it depends. Smaller proteins, larger proteins. Depends if they're polar or not polar. We're talking about
a tough question because if all the protein came out freely of these vessels, then lymph would actually have a higher concentration of protein than blood, because blood had these red blood cells that were taking up space, and so the protein was, so to speak, diluted by this huge amount of red blood cells. And now here it won't be diluted by red blood cells. But actually there's less protein out here in the lymph, and that's because water gets out so much more easily from these capillaries than protein that you end up with fairly dilute fluid here. So proteins have a kind of tough time getting out, and certainly some of them do get out, and so we'll draw those here, but it's much less than are in blood. And so we end up with about a half to a third the amount of protein in lymph compared to blood. So lymph has about a half to a third versus blood. Let's draw that like that. Another thing we can ask ourselves is what kinds of proteins are going to be in this lymph. Since we said that there were so many different kinds of proteins in the blood, which ones are going to get into the lymph? And actually, it's going to be the smaller ones, generally. The smaller ones are going to have an easier time getting through these holes. And so we can say, for example, that the ratio of a small protein like albumin over a large protein like an immunoglobulin, I'm just going to write Ig, these are antibodies. They're generally bigger than albumin. So the ratio of albumin to immunoglobulin is going to be bigger in lymph than it will be in blood. And the reason for that is what we just said, that smaller proteins have an easier time getting through than large proteins. So even if you have less albumin overall in lymph compared to blood, you'll have a greater albumin over immunoglobulin ratio. And let's actually pause here a moment before we move on from talking about protein in the lymph, because it's actually very important that there's less protein in the lymph than there is in blood. Because if you watched one of the earlier videos, you remember that we said that actually the way that fluid gets squeezed out of the capillaries is not so straightforward, because what happens is first some of it gets squeezed out, but then some of it gets taken back up. And the reason why some of it gets taken back up is because as you travel down the capillary, the hydrostatic pressure that pushes this fluid out goes down. So there's less pressure pushing it out, but there's still some pressure pushing it out. So why is some of this fluid going back into the blood vessel? And the reason is that there's a higher concentration of things like proteins in here. And that higher concentration makes the blood more, this is going to be a scary word, but more osmotically active. And so there's a higher osmotic pressure pulling fluid back in, exactly because you have more protein in the blood than you do out here in the lymph. And so it's very important that you do have more protein in the blood. And now I'd like to ask you a question, which is how much lymph do you think is produced per day? So the amount of lymph that's produced is the amount that's squeezed out of these blood vessels minus the amount that's taken back up. And so how much do you think that adds up to in an entire day? So how much lymph do we produce? And let me give you a moment to guess. So how many liters? So come up with a number, the number of liters of lymph that we produce per day. And the answer is 3.
Oh.
So we make about 3 liters of lymph per day, and that's all filtered out through these capillaries. That's a word people like to use, filter. And actually, it turns out that the amount that actually comes out first is about 20 liters. And I'm going to draw it small because these are really small details that you don't need to know. But about 20 liters is squeezed out, and then about 17 liters comes back in. And so that leaves a difference of about 3 liters that comes out per day. So this is per day. The final thing that we should really mention is that lymph has a different composition depending on where you are in the body. So let's quickly look at a human body so we can talk about how lymph might differ from place to place. So here's a human. And one thing we talked about was how in the small intestine over here, your lymphatic vessels, which there are called lacteals, are taking up a lot of fats, a lot of chylomicrons. And so as you might guess, the composition of lymph coming from there is going to be much higher in those chylomicrons, which are collections of fats. So there you're going to have more fats in the human body, so we can talk about how lymph might differ from place to place. So here's a human. And one thing we talked about was how in the small intestine over here, your lymphatic vessels, which there are called lacteals, are taking up a lot of fats, a lot of chylomicrons. And so as you might guess, the composition of lymph coming from there is going to be much higher in those chylomicrons, which are collections
In
of
where?
fats,
Intestines?
depending on where you are in the body. So let's quickly look at a human body so we can talk about how lymph might differ from place to place. So here's a human. And one thing we talked about was how in the small intestine over here, your lymphatic vessels, which there are called lacteals, are taking up a lot of fats, a lot of chylomicrons. And so as you might guess, the composition of lymph coming from there is going to be much higher in those chylomicrons, which are collections of fats. So there you're going to have more fats. Whereas when you go to the liver, and this is not something necessarily that you know or should know, but it's an interesting fact, the liver produces a ton of proteins that end up going into your blood. And one of the ways that they get them into the blood is to put them into lymph. And so your lymph coming from the liver has a much higher concentration of protein than your lymph coming from elsewhere. And it actually can get to as much as 10 times as much. You have 10 times as much protein in the lymph coming from the liver compared to other places. And so this number here that we gave, 1/2 to 1/3, is really just an average of all the lymph all over your body, because the protein content can vary widely from place to place. As we know, eventually all the lymph vessels, including the lacteals coming from your small intestine, they all join up and they come up your body, and also the ones coming from the liver will merge and join and come up and travel up through the body, and eventually they'll be put back into circulation, and that will be here in the veins up here, which I'll draw in blue, even though it's getting a little confusing there. Drawing them in blue because we generally draw veins in blue, and those merge and go to the heart. So all these different lymph fluids with different compositions will come together and go back into circulation. These different lymph
All right, let's take a 10-minute before we start the questions. Oh, man, it's getting hot. I don't know. %40 humidity. Is this accurate? I don't think that's accurate. There you go. I don't think that's accurate. Is that accurate? Oh, 36% humidity. Jesus. Okay. All right, I'll be back. Take a 10-minute. I can't. I don't want to be in, especially my room. My room is always the hottest. I'm getting cooked. I'm getting literally cooked. Hold on. Hold on, Mom. Sure. When the glasses are hot. Contains carbohydrates. Interesting. No detectable amounts of free carbohydrate. I don't know. Concentration of fatty acids. Repeat. Okay. The jugular vein. I don't know why I would go to the jugular vein for. Breathe. Right? Um, hmm. Maybe we'll see. The jugular vein. But if it's already at our interstitial spaces, why am I thinking more like the GI tract or like the intestines? Oh, never mind. Between structures. Never mind. Jugular vein. Actually, that does make sense. Never mind. Um, and then flow. Decrease osmotic pressure. I'm not sure, maybe. Decrease cardiovascular capillary permeability. Decrease permeability. If we decrease permeability, then there's probably not going to be any flow, right? More goes out. Some goes back in. Must mean that it means that outside we have higher solutes. How it increases flow. Is it pressure over volume? Was it pressure over volume? I don't remember. I think so. Wait, what? All right. Was something like that? Maybe, possibly. Let's see. If we increase the calculated pressure, potentially, but it's not gonna burst it. It's gonna burst it. I don't think so. They already had kind of low pressure to begin with. Increase the osmotic pressure. Excuse me. This sounds pretty good, I think. I don't think it's going to be decrease the pressure. Might be A, essentially. Interstitial fluid colloid osmotic pressure. Interstitial. Actually, maybe not. I don't think so. Yeah. No. Oh, it could be. Depends. Depends. Interstitial fluid. Interstitial fluid. Which is the interstitial fluid? Maybe not. I don't think so. I don't know. I'm gonna go with C. Well, whatever. What was the other one that I thought? Could be A, potentially. I could just be wrong. Increases pressure here. Maybe actually that's probably the one. I mean, that's probably the one. It's probably D. Why did I do D? What the heck? Hello. What are you thinking about, my dude? Yeah. No. So we know that the looking for the one that's not. So this is this is this is A and D individual epithelial cells forms a closed loop. Forms a closed loop. I know the cardiovascular system is a closed loop. That would include veins, right? Epithelial and basement cells. I think that is shared between both, right? Tunica media, tunica intima, tunica externa. I think it's A then. This is likely. This is likely. Okay, this is also likely. I think this is. This is right. This is. I think D. We have B cells and T cells at the lymph nodes. That's what I remember. So it's gonna be A. That's messing with me. Okay. Lymph from which of the following parts of the body does not? To the thoracic duct. I think parts that's already coming from the head. But is that true? Either it could be A, or it could be D. I don't think B or C make any sense for the answer. I'm going with D. Okay, let's go with A. Oh, what the heck? Wait, what? Left, right, right. What the heck? What are you talking about? The left arm. Okay. Sure. From the right lymphatic duct. Well, our heart is mostly situated on the right side. I mean, left side, a little bit below. So, if we're on the right lymphatic duct, but you gotta go through the right into the right subclavian and the jugular vein, right? And then go. Yeah. I think A. Okay. Let's watch this guy. Yeah. Yeah, that's what I thought. What is that? What the heck is that? Oh, that's a shoulder. That's a shoulder. What am I looking at here? What the heck? Am I getting where? What? Yeah. Very. Thank you. Kindly. Thank you kindly. $14. If we're spreading through the what? If we're spreading through the what? Seriously? Um, over the course of the day. Um, I'm not sure if they do or not. Maybe A. Um, excuse me. Say B. Ooh, okay. Um, lymphatic protein. Lymphatic protein. Well, I didn't. That's fine. Okay. Okay. All right. Um, um, Probably Anki's next, I think. It might be all we can do today. I really don't want to go too late. Try to be a little better. Yeah, there's so many things to watch. Okay. Yeah, I think we do Anki next. Let's actually browse. Make sure we add anything we need to add. Hold on. If it's there or not, I don't know. Probably not. I think I checked last time. I didn't find anything. Oh, will you? We did find a couple of things. It's mostly because the immune system is bundled with the lymph system, so I don't think I'm going to find like a lot, to be honest. So we can just leave those there for now. Yeah, that's fine. Okay, let's put up Anki for now. And we'll do this, and that might be it. Hello. Hello, Hamza. Yeah, let me so I wonder if I should change my name. Maybe I can try. And that's fine, just leave it. But let's just change this, right? Yeah, that's fine. An hour, 40 minutes. I don't think I have any time. I think the best thing is just Anki today. Okay, give me 10 minutes and we can start. Yeah, yeah. All right, let's get back. Look at all these cards. I think we'll start with this one. Let's go from the bottom and start top. Consciousness, cognition, emotion. Consciousness, cognition, emotion, self-awareness, I guess, something like that. Whomst. Oh, when I say get some air, there's a bunch of mosquitoes. Suck my blood. Suck my blood. Decrease in the motor stretch reflex. Mm-hmm. The hypothalamus. The hypothalamus. Sometimes you have inhibitory, clear that one. Sending it to the what do you call that muscle group? Well, yeah. Okay, and then he's gonna drop. Yeah, afferent will go towards the CNS. Well, towards the send the signal back towards the brain. Synapse in the spinal cord. Okay, so synapse in the spinal cord. Synapse axon. Send back out to the lower motor neuron efferent. And then if it sends it back out, it's going to go to the front. To the front of the spinal cord. And you're going to have two synapses or quadriceps, yeah. So the quadriceps will be contracted and they'll be depolarized. You get inhibited. Excited, I guess. Excite, contract. And the hamstring, that's the word I'm looking for. The hamstring will be inhibited. Yes. 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 Dorsal root ganglion and the afferent neurons. Yes. Increased response in the muscle stretch reflex. The genetics. Ooh, I should have. I can't really take a look at those. Control the lower motor neurons. Yeah. Contract. Pressure. Yeah, I was gonna say pressure. Increase the pressure of the gas. Oh, okay. Physically pressing. Damn. I thought we were squeezing it. Somebody physically pressing down. Oh. Okay. Yeah, okay. Sure, let's go ahead. Lowering the membrane potential. K plus. Somatic. Somatic is voluntary. RNA dependent. RNA dependent. RNA dependent RNA polymerase. Is it RNA dependent? RNA dependent RNA polymerase. Now, thinking about something else. RNA dependent DNA polymerase. RNA dependent DNA polymerase. Hold on.
Hello?
Hey, Katroff. End of July, but I'm trying to see if I can reschedule a little bit for August, but the dates are really full. So, yeah, we're gonna have to speed it up, dude. I'm feeling a little bit more confident if we get through. Well, once we get through this, we hit up into the next sections. I just have a feeling it's gonna go a lot faster. At least that's what I'm hoping for. But we'll see. I don't know if you can even hear me. Well, whatever. All right, let's continue. Yeah, water. Water molecule. Wait. Oh, water molecules lost. Well, water molecules used. The same thing. Wag. Uga. Equilibrium constants. KEC is product over concentration of products over reactants. AUG, chlormethionine. There's a couple of things I'm missing, just a couple of things. If we finish tomorrow, which I think we can, maybe we take a little bit extra time to review the things that I think I'd like to go over. Haploid, glycine, peak energy potential gases, potassium channels open while the sodium channels close. WAG, UGA, phosphate, ribose. 1, 2, 3, hydroxyl on the third carbon. Leave the cell. Leaves the cell with help of breakdown of ATP. 3-dimensional tertiary structure due to the backbone of the amino acids and chemical reactions. Ooh, secondary structure? Wait, secondary structure? Is that right? Oh wait, maybe I'm thinking about it wrong. The backbone. Actually, I think it is right. Yeah. The backbone is the amino group nitrogen, and the carbonyl carbon covalently binding peptide bond, and we also have okay. Yeah, okay. Hydrogen bonds and backbone atoms. Sure. Secondary. Proton motor force. No, chemiosmosis. Proton motor force. No, accident. One strands. Leading strands. Myosinus. I don't even know. I don't think. Well, I'm not even here yet. What is Spencer? Proline Pro. Proline Pro P. Proline Pro P breaks alpha helices. Is a rigid structure found in beta pleated sheets. Causes sharp turns and nonpolar hydrophobic. Yeah. Secondary structure. Reverse transcriptase, which is RNA-dependent DNA polymerase. Small molecules and nonpolar molecules. Nonpolar, small and nonpolar, like O2 gas. What are we talking about? Okay. Yeah, small nonpolar O2 gas. Water does still, but it's just slow. Ethanol does, it's very slow. Large molecules do too. Polar molecules like glucose do not need to be transported, and so do cations and ions. Okay. Phospholipids. Transition state. It lowers, enzymes lower the activation energy. Yeah. Protein channel. Lyase. Yeah, breakdown. DNA polymerase. Cooperativity. Similar to body fitting. Cooperativity. Sodium potassium pump. Leave. Coordinate structure, 2 alpha helix, two alpha subunits and 2 beta subunits, each containing a heme coenzyme. No, is it a coenzyme? No, it's prosthetic group, right? Prosthetic group. Hopefully I see that again. I'll do that later too. Cooperative binding, cooperativity. Pressure. At. If it's taut, it's uptight. If it's uptight, so many bugs in my room, man. What the heck? Where are they getting in from? If it's taut, it's uptight. If it's taut, it's uptight. If it's uptight, it's not bound. It cannot. It has low binding affinity to oxygen, and it has none bound to it. Why are you so uptight? It's only a game. Why you have to be so mad? That's a good one. The potassium check. Wait. The potassium channels begin to close. But I do so pretty slowly. Glycine, achiral. It's the only achiral. Yeah. We add water. Water molecule. Extracellular, like bacteria. Oh, let's go. Yes. All right, hold on, guys. Oh, it's like some sort of. It's fine. Alright, I'm going to bugs crawling on the walls. I'm doing pretty good. Oh, be grateful. Be grateful. Delta G prime is equal to negative R times T times the natural log of kek. Negative R times kek. And then R is 8.314 joules over moles times Kelvin. That was a good one. Anyways, 3 codons, 3 stuck codons. Relaxed. It's had a couple glasses of oxygen. So it's relaxed, you know? Relax yourself. Take some oxygen. Relax yourself. Take some oxygen. Of the innate skin stomach acids. Intracellular viruses of cancer. Yeah. Don't worry, I'll watch your videos. I'll watch them all, John. Action potential. And a left shift. Yeah. Oh, that's so small. Okay, a lower carbon monoxide, a higher pH, or lower temp. Reduced is higher CO2, lower pH, higher temp, or increase 2,3 BPG. I forgot what the name for it was. Oxidative phosphorylation. Secondary structure. Acid digest. Parasympathetic. Constrict. Constrict the pupil. Stimulate salivation. Constrict the bronchi. Slow down the heart rate. Stimulate peristalsis. Move food and fluids down through to the digestive tract. Okay. Push fluid down. Push food or fluids down to digest. Stimulate the bile release. Fat. Digestion and absorption. I don't know what this one is. Oh, secretion of adrenaline. This list not even written down. Contract the bladder to hold in the pee. Inhibit bladder contraction. Wait. Contract the bladder. Inhibit bladder. Am I thinking about that right? Bladder contraction holds pee or releases pee. Bladder contraction releases pee. It's kind of interesting. So when we're in fight or flight, we're going to release pee. Interesting. Okay. Okay. Um, hydrophobic effect of proteins. Which amino acids are hydrophobic? Glycine, leucine, alanine, methionine, valine, isoleucine, proline, phenylalanine. Hydrophilic. Hydrophilic. Asparagine, serine, serine. I don't think cysteine is. Wait. Yeah. Oh, yeah. Glutamine. Wait. Yeah, glutamine. I don't think cysteine is. Asparagine. 309. Histidine. I think histidine is slightly polar. Is it slightly polar? Lysine for sure. Arginine. And I think tyrosine. Maybe. Yeah, tyrosine. And aspartate, and glutamate. Hydrophobic ones, right inside plasma membrane. Folded inside or on the outside? Folded inside. Okay. Condition state lowers activation energy. It's a nucleus that contains a set of each homologous chromosome. Pair. Okay. So what the heck? Pair. Yes. Cooperativity. Hemoglobin is positive for activity. This one. I don't know. One multiple. Cytosine. Plasma membrane lipids are generally cholesterol functions to increase or decrease fluidity and help help stabilize the cell membrane. Tot. A right shift. A right shift. Yes. Yes, that's how I'm thinking about it too, buddy. That's how I'm thinking about it too. It's the depolarization. DNA polymerase. And the mitochondria. Cadet. Cadets, face to the right. Cadet, face to the right. And it's like oh, what's the? I don't know. I forgot. Maybe. Well, I'll probably. What do they call them? Marching movements. Marching movements. Right face. Right face. Left face. Halt. Right face. Left face. C is CO2. Right face. Parade. Parade. Attention. Relaxed. Take some oxygen. B cells need more immunity, which are extracellular, which are for bacteria. Unless I got that wrong. Oxidized. CNS. Electron transport chain occurs in the mitochondria. Thymine. Size, charge, structure. Non-protein molecule. cofactor. Yeah, well, okay, so it is a cofactor. Left shift, CO, increase in pH, or decrease in temp. Equilibrium. Dehydration or hydrolysis reaction. Yes. Post-transcriptional modes. The stimulus forces the neuron to threshold potential. Stimulus and it slips in. Very fast. Concentration. Kind of sort of is. Think about it. To form disulfide bridges. Disulfide. Heat can disrupt these bonds. All these little comments are like, I think, pretty important to also keep in mind. Sympathetic. V equals V max times the substrate concentration all over Tn plus the substrate concentration. And then, yes, all this stuff. Photons into the inner mitochondrial matrix. Oh, intermitochondrial membrane space. Backbone. Electron donor. Electron donor. Are generally cholesterol. Cholesterol are precursors to steroid hormones. Not specific. Humoral immunity. Taut. No oxygen. Hemoglobin not bound to any oxygen. Okay, unbound to oxygen. At equilibrium. phosphate. 1 to 3 phosphates. T cells relaxed state, down to oxygen, high favorite. Hyperpolarization or the refractory period. Okay, competitive inhibition, uncompetitive inhibition, not competitive inhibition, uncompetitive, KM no change, Vmax goes down, uncompetitive, KM and Vmax goes down. Competitive, KM no change, yeah, Vmax no change, KM increases. Any plus shadows open, more any plus slits in. To the Golgi. We go to the Golgi. Head on out to the Golgi. Cadet face right. Cadet right face. What's A? A, okay, CO2. We did increase in time, we did exercise. What was this one? 2,3 DPG, same thing as 2,3 BPG. A. 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 Seriously? A. Oh, A. Decrease in pH. Okay, acid. Yeah, same thing. Almost got me. A right shift. Signalers and cell recognitioners. Oh, never mind. Well, receptors and channels. Spontaneity. No memory. No memory. 2,3 DPG or 2,3 BPG. This is a right shift. Cysteine brushes the hair with a short sulfur handle. Cysteine sissy. There you are. Beautiful cysteine. You are polar. Ah, sneaky. You are polar. Oops, I should know that. That's probably pretty big. I think then, yeah, they're all actually. Okay, never mind. Okay, yeah. Yeah, okay, sure. Cytosol, very specific. Some, autonomic? Right. Okay. Yeah. Autonomic. Yeah. Smooth muscles. Okay. Increase in CO2. E. Oh, exercise. Um, uh, uh, Sympathetic, parasympathetic. Repolarization. Timing. Autonomic nervous system. Temp. Specifically, an increase in temp. Facilitate diffusion of light matter. Um, Alanine, ala A. Coenzyme. Cofactor. Disulfide. Rich bonds. Heat counterceptor bonds. Dehydration. Glycolysis. Backbone. Intermembrane space. Relaxed state binds to oxygen, bound to oxygen, not bound to oxygen. Acid. 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 Receptors and ion channels. T23 DPG or T3 BPG. E exercise. D10 increase in 10. A cofactor such as the one in heme. Let me take a 5-minute break. Let's take a 5-minute. I might already run to like 12 something, huh? I think tomorrow we'll completely finish though. At least this section. And I want to wrap up some gaps. So maybe we'll finish. Well, we will finish. And then I'll wrap up some gaps and some little extra content stuff. Tomorrow will be a good day. Tomorrow will be a great day, I think. I hope. I'll be back. Got it. Thanks. Has anyone ever heard of Darude sandstorm? Darude sandstorm. Yeah. Yes, sir. I don't know why. It honestly feels like it's cycling. Whatever. Good morning. Yeah, okay, buddy. I like the little exclamation marks, like, uh-oh, you don't know this. Splicing. Okay, what is it? Kidneys. Yes. Yes. Oh, temperature's cooling down. That's nice. The summation of all the ionizable groups in the amino acid dependent on their pH of their environment. Excellent. Endoderm, not mesoderm. Yes. Okay. G2. Oh, man. Table something else. Whatever. Um, um, yeah, okay. I'm not sure. Okay. Part cap, polyate, spicy. Skin, teeth, hair, skin, teeth, hair, eyeballs, I think, and nervous system. Oh, nails. What about the nails? Spicy or something? Tennessee, one of its ingredients. Mm-hmm. I think it's basically right. Neutrons, parathyroid glands, fusion of like so. Genetic different with parents. Introns. Crafted from. Oh, that's interesting. Well, crafted from uh, DNA, DNA, translation, protein. Protein goes into the red blood cells. Proteins and cofactors. Similarly structured, code for the same trait. Genes code for the same trait. Let's see. 46 2M. No, plants. A cycle. To the left. 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 It occurs in the blood of the what? Yes. In the lungs, we want to go. We go basically lungs to tissue at that point. Blood of the capillaries surrounding the lungs under conditions of low CO2, low temp. Mm-hmm. Mm-hmm. Again. Proteins and cofactors. Repeating segments of the chromosome. repeating processes. In nature is the protein. Maybe 55 millivolts. Oh, wait. Negative 70 millivolts. Introns are sequences of sequences of RNA that code for proteins or non-coded regions of genes that are not translated to proteins. Yes. Occurs in the blood of the capillaries surrounding the lungs. The blood of the capillaries surrounding the lungs. Heme. Okay. I'm thinking cofactor. Yes. Lungs. Multiple chromosomes within a pair. Example, Down syndrome. Oh wait, never mind. No, this is not. I thought it was Down syndrome, no? Let me see. What a mess. What a mess. Yes, it is. Spinal cord. Vertebral column. Cofactor. Growth and development. Left shift. Left shift. We have low temp. High CO. Oh, wait, low temp. High pH. Low. Low rider. Low rider. I don't know. Low what? Low temp, high pH. Low CO2. Yes, low CO2. Splicing. Exons. Okay. And toxic chemicals. UV radiation and 6 engineering radiation. Oh, they left here repair mechanisms. Yeah, that's true too. The nodal cord. The nodal cord. Double layered organelle. transport oxygen to other cells, to the tissues cells. Okay, homeostasis, influencing enzymatic processes, orchestrating cellular expression. All right. Zone mining and release of oxygen. Okay, yes. There's that too. Low CO2, high pH. Low CO2, high pH, low temp. Low temp. And we're in the lungs. And the blood capillaries. Oh, yeah. Below the capillaries surrounding the lungs. Transition state or EEA. Chromosome location. Twenty-three. All this stuff. I think I'm fine. Just keep bringing it up. Just move it along. ADH. Wait, ADH. AH and ADH. No. NAD and FAD. NAD plus and FAD. Muscle development, the air repair, DNA rep, and gene regulation. Sexual reproduction. Non-coding regions of genes. Introns. The mesoderm. Substrates. Enzyme. Positive conformational change in its protein structure of the different subunits, making it more likely for other substrates to bind. Higher for enzymes. Capillative splicing. NAD plus FAD. A change in the final product of protein expression and can lead to disease states. Replication fork. Facial bones, Schwann cells, adrenal medulla, facial bones, Schwann cells, adrenal medulla, and what? I forgot. Melanocytes. Melanocytes. The transformation from pre-mRNA, removal of introns. I think I've been saying that like 100 times now. Forms a zygote. Okay. Cooperativity. Oh, proteins and cofactors. Okay. Causing. Okay, nucleotide excision repair. Condition like xeroderma pigmentosa, causing increased sensitivity to UV radiation and melanoma or cancer. Cancer. Nobody likes cancer, man. Cancer sucks. Embryonic development begins with fertilization, also known as fertilization zygote, germ cells. Okay. All right, dude. Peak of the energy curve. Here's red? What are we talking about here? Okay. Proteins and cofactors. 3.5 right? What? 3.5 right? 5 prime to 3 prime. DNA polymerase can't read it. This always messes me up. I mean, DNA polymerase reads from 3 prime to 5 prime and synthesizes from 5 prime to 3 prime. What does it mean it can't read the strand from 5 prime to 3 prime? What are you talking about? What are you talking about? Sure. Crafted from. Crafted from. Protein cofactors. Differentiation, cell signaling pathways, interactions. Two cents. Neural tube. Introns. Exons. Okay. Fibroid cap with the fibroid ends. Shift to the left. And the blood of the capillaries surrounding the lungs. K energy max. Sodium potassium pump. Polyethyl, recommend coding regions of DNA will code for proteins and will be translated into proteins. Also by blood vessels. So we're talking about the delta G prime. That is a spontaneous, known as exergonic. Muscles, blood vessels, connective tissue, bones, kidneys, and reproductive organs. Diploid. I am a somatic cell. Somatic cell. Yeah, so I'm diploid. Transformation from pre-morning to mature morning. and the addition. Okay, yeah. Five-point cap and polyetail, three-binding. Ecofactory. Few items. Center. Aspartate, most similar is glutamate. Glutamate. Equilibrium. Low CO2, high pH, and low temp. Look at this. Yes, neutron serve. Neutron serve as alternative splicing, kind of like a little bit of genetic diversity, epigenetics, you know that. Organizational splicing, epigenetic was organizational splicing system, and DNA, failure DNA repair mechanisms. Low CO2, high temp. Low CO2, high temp. Whoa, what? Stop tape. Low CO2. Low temp, high pH. Yeah, okay, right. RNA-dependent DNA polymerase and is used in retroviruses that return negative sense RNA strands into the complement that will then go from mRNA to proteins. mRNA. Sorry, the complement DNA, and then moves forward. Bind to oxygen molecules, and oxygen atoms, and transport it to cells that are low, tissue cells low in oxygen. Right, listen, yeah. I need everything else. Enhancing its functionality. So the mutations, we have point mutation, missense mutation, not mutation, point mutation, no change, and the amino acid sequence, the protein, amino acid, yeah, and the sequence for the codes for the amino acid, and missense there's a changes the amino acid, nonsense codes for stop codon, which will, premature stop codon in the sequence. Yeah, there you go. Yeah, a couple other stuff too. That's cool. Oh, okay. I thought I said point mutation. Okay. Yeah, that's fine. We got it. NAD plus FAD. Ectoderm, mesoderm, endoderm. Increased binding affinity. Somatic cells. with the second law of thermodynamics. Hydrophobic effect of protein structures. Facial bones, Schwann cells, adrenal medulla, melanocytes. Now I feel like I'm missing one. Facial bones, adrenal medulla, Schwann cells, melanocytes. No, actually not. Homeostasis, a couple other stuff. Homeostasis, enzymatic processes, orchestrating cellular respiration. Homeostasis, enzymatic processes, cellular respiration. Enzyme becomes saturated. Substrate concentration and velocity of the enzyme. Okay, yeah, substrate concentration and reaction rate. This is carelessly represented by the equation below. E enzyme. Right. Neuronal process. Homeostasis. Enzymatic processes. And homeostasis, enzymatic processes, and cellular respiration. Non-protein. What? Are translated by? Are translated by? Yeah, are translated by RNA ribosomes. Okay. Tyrosine, serine, 309. Okay, yeah, to upregulate dendritic function, tyrosine, serine, 309, and then if you use DNE, then it's phosphorylated effect. It's really bad, as the voltage, as the event. Now, starting point? Oh, okay, voltage. Here's the voltage. Yeah, there you go. I see removes. Proteins and cofactors. Protein coding regions of DNA. Cover proteins. Okay. Yeah, okay. Previous genes translated protein. The refractory period prevents the backflow of propagation by ensuring that we have unilateral flow of the voltage events, right, of the action potential firing down through the exon. And it ensures this by having those channels, sodium channels, be closed because they've already fired, essentially, right? Yeah. Low CO2, high pH, and low temp. Vibrant cap polytip is a process where we synthesized DNA from RNA, RNA-dependent DNA polymerase, turn that mRNA into its complement of the non-coding templates of the non-coding strand. I forgot. I missed. Or the I think. Anyways, cofactors are non protein. Crucial for protein's function, advancing functionality. Processing specimens. Ribosomes. Homeostasis, enzymatic processes, and cell respiration. Okay. Oh man. Drop this. Background cap. Polyethylene 3 primary. Into Michael something. Chylomicrons. Chylomicrons. Oh, those are my micelles. Micelles. A micelle. So you're a micelle, aren't you? Okay, short fatty acids are absorbed across the intestine into the blood. Oh, man. I need something on my head. Oh, there you go. I found it. Some chylomicrons. Compose the cytoskeleton. Cytoskeleton, structural protein. Extracellular. What's the extracellular? Okay, cytoskeleton. Protein scaffolding. Structural anchoring proteins. Results from insertion or deletion of nucleotides in the sequence. Nucleotides, yes, sir. Chylomicrons. Oh my goodness. Chylomicrons. Oh, again, this. I don't like this stuff, man. Why? Darn you, bacteria! I don't like you. I don't like you. And and removes itself from the segment of DNA. The lymphatic system, the lumen, monoglycerides, and the fatty acids, smooth ER. Wow, there's a lot of stuff going on. The Golgi on the capillary, endothelial cell. Wait, endothelial? Endothelial? Oh man, I'm not sure. Is it sorry, it's endothelial cells. Chylomicrons transport lipids across the lymphatic system. I think that's what I said, right? I think so. 2011 Pearson education. Look at that. 2011. 2011 Pearson education. Chylomicrons. I keep saying chole. Of the cerebrum, of the forebrain cerebrum, frontal parietal temporal occipital, inducible operon, fluidity and stability, lymphatic system. Wait, lymphatic system. Yes. Oxidoreductase. Also alcohol dehydrogenase. Alcohol. I think it's alcohol, right? Oh my goodness. DNA polymerase acid with the gun strand 30. DNA replication. Cortisol. What? Oh, my cells? Oh no. Chylomicrons. Kylo. Let's do a pronunciation, I guess. Chylomicron. Kilomicrons. Okay. Wait. McKenna's Benton. Curve shape. Parabolic. Jesus. Hyperbolic. Not just parabolic, it's hyperbolic. Wallow, unstable. Wallow. We have the hypothalamus, limbic system, basal ganglia, and the cerebral cortex. Yeah, 4, 5. Yes, sir. Sudden blotting is used to detect DNA. In the DNA. Transport lipids through the lymphatic system. Chylomicrons. Scans for sarcoma. The frontal lobe. That's my frontal lobe. Hello. tRNA brings amino acids to the ribosome. To the mRNA. Into the ribosome. That's fine. Reads and synthesizers. Proteins. Why did you take minutes? Lactose binds to the lactopressin. Breaks the bonds. In order to separate the two strands. Two DNA strands, yes. Activate. DNA sequencing based on DNA sequencing. Based on the way they fall during the body. Selective incorporation of chain terminating dideoxynucleotides. Based on the selective incorporation of the chain terminating dideoxynucleotides. Scans for sarcoma. Lays down and for methionine. at the PC. So it also scans for touchscreen. A non-functional protein. Oh, pretty sure something. Translation. PCM is a amplification technique. Oh, fast and expensive. Okay. Oh, good. Seriously, this one is mental health. It's termination of the antioxidant nucleotides. Yeah, okay. DNA sequencing. Chain terminating antioxidant nucleotides. Stress hormone. The forebrain. Uniform negative charge. And then a thermal. Thermal. Let me see the word. Thermodynamically resistant. Heat resistant. Thermostable. Okay, thermostable. DNA polymers. Yeah, heat resistant. A little bit heat resistant, I guess. Well, heat resistant. Yeah. Thermostable is better. Cytoskeleton. Cytoskeleton. What's the word? What's this? Anchoring proteins. Anchoring proteins. Yeah, collagen, elastin, keratin, actin, tubulin. DNA sequencing based on terminating chains of dideoxynucleotides. Terminating chain of dideoxynucleotides. Fluency continues no matter pyridines. Okay. Furines A to G 2. Pyridines cut 1. To leading strand. Growing strand. A growing strand, yeah. Directly. Look at that one. Or assembly into chylomicrons. The down system. feedback system. Metabolic metabolic molecules and small proteins. Glucose. New sequence. New sequence of proteins that together run. Type bonds. Yeah. That's kind of cool. Agarose gels has small pores which used to separate nucleic acids. Then it has larger pores which are separating proteins. Wait, no, it's backwards. Wait, did I say that right? I don't think so. No, microns. Microns. Kilomicrons. Wow. It's not like it is like no. See, I think so. It's one of them. Tomato. Triggers the expression of a gene or alcohol. Is hydrogen. Will determine its shape. Yeah, what gives it some of its shape due to the backbone and hydrogen bond stabilization. Local folding, coffee elasticated fitted sheets. Again, hyperbolic. Chylomicrons. Jesus. Kylo. Chylomicrons. Tertiary. Hydrogen bonds, ionic bonds, and sulfide bonds, hydrophobic interactions. At increased temps, high temps, peripheral nervous system, which is due to side chain interactions stabilized by hydrophobic. The protein shape. But anyways, it's stabilized. It gives this protein, but it's stabilized by hydrophobic interactions and sulfide interactions, hydrogen bonds, and ionic interactions. Hydrogen bonds, other ones. Yeah. Yes. Activator. Is stabilized by hydrogen bonds, including beta pleated sheets and alpha helices. Yeah, stabilized by hydrogen bonds. proteins. Polymicrons. Chiromicrons. Complementary. More social to positive sense RNA. Yeah, that is true. It is positive sense RNA. Acts as mRNA. RNA dependent. Oh wait, hold on. Oh, no, that's a different thing. What is this for? Maybe different viruses on. Yeah, reverse restrictors, right? Okay. Fast and inexpensive secondary structure. Stands for sarcodon. What the P site is. Methylmethionine. Formylmethionine. Formylmethionine. Speech, executive functions. Has a motor cortex. Something about regulating emotions and a little bit of speech. A little bit of speech. Oh, impulse control. Very well. Impulse control. Motor cortex. Yeah, that's right. Is it stress hormone? PCR relies on a thermoregulating. Thermostable. Yeah, that's fine. The coronary structure proteins is yeah, I mean it has the subdivided by it's divided by its subunits, right? Stabilized by I think the same thing as a tertiary as well. Yeah, basically, and it contains interactions between the different peptides. Good peptides. Okay. What is that? What the heck is that? Interesting. Three D shape. Tertiary. Cytoskeleton, anchoring proteins, and the extracellular matrix. DNA sequencing based on chain terminating dideoxynucleotides. Chain terminating dideoxynucleotides. Bodies a method from DNA or RNA. DNA or RNA or protein fragment separation technique that So pretty good job. We just forces a line into it by number. Yeah. Producer. Unical coils. Clockwise coils. Clockwise coils. Uncompetitive inhibition. Uncompetitive inhibition at the ES complex. No, it's okay. Decrease. During denitrification, the nucleotides also depleted or amino acid is changed. Or you stop. And the codon is introduced. It's a bigger structure that can interrupt afterwards both instructions. Oh, secondary, yeah, okay, secondary. Stimulus, glutamate, occipital lobe, cones, clockwise cones, cones, fatty acid chain, lipid chains, long, intercellular transports, small bores, nucleic acids, large bores, proteins. No, it's the other way. Large and then small. Okay, it is what it is. Directly. It's fine. This one is one molecule. Over inducer is one molecule. Last for tree transcription. Chemical proteins. In charge of transporting lactose. Parietal lobe is associated with touch, sense pressure, temp, pain, and spatial processing. Long chain fatty acids used to amplify segments of DNA, specific targets of DNA. 40S, denaturation to cleave, reduce, parietal PCR, chylomicrons. Low temps. Pattern is stabilized by hydrophobic interactions, mainly, and gives it a shape based on the side chain interactions. Anyways, the stability also includes disulfide sulfide interactions, ionic interactions, hydrogen bonds, hydrophobic interactions. Yeah. Is stabilized by hydrogen bonds, including alpha helices and beta pleated sheets. Due to the backbone, I think. Right. If I can find it. So, color icons. Is made up of peptides and subunits. The interaction between the peptides and protein can be multiple subunits. Glutamate is basically by the same things as surgery, and it's due to continued interactions between the peptide and has multiple subunits. Yeah, that's fine. Agarose gel has large pores used to separate nucleic acids. Polyacrylamide has smaller pores used to separate proteins. They code for they code for proteins that help in the transport of lactose. Chain fatty acids. All right, guys, I'm gonna go sleep. Hey, Jack. Yeah, the exam is the exam's end of July, so we gotta speed things up. Anyways, have a good night, everyone. Thanks so much. Take care. Hope everything's going well in your life. Hope your studying's doing good. Hope you guys ace your exam. Hope you guys ace your exams. Good luck. Good night. Peace.